top. And in this environment, I would love to welcome our honorable guest speaker, Dr. Lakshmi Ravishankar Pradam, and our principal, Dr. Arpan Bharadwaj sir. He is facing tough time too in the college and because some people are afraid that they are also found COVID positive in college, one person. So difficult times for him too. Dr. Pare, sir, namaskar, head of department, sir.
Namaskar, sir. Namaste.
Namaskar,
So,
sir.
I'm audible, sir.
You are very much audible, sir. You're looking very fine. What a lot of light on your face.
It's okay, na?
Yeah, it's fine. Dr. Kalpana
Thank
Singh,
you.
thank you for hosting this seminar. I mean, it's a lecture, and my regards and love to all the students and faculty, those who have joined, all those who can hear me. It's been a long time since I have seen them. So my regards, my all the best wishes to all the students. Take care and be safe. And formally, Dr. Lakshmi Ravishankar will be introduced by Dr. Kalpana Singh later on. But just a little bit of a few words from me regarding. I was just going through her profile, and I'm so happy to see it. Because on her wall too, she has a lot of words for her teacher, Dr. G.K. Trivedi. Right? I'm right, ma'am.
Yes, sir. Professor
So my
Trivedi was
regards
my
to your
guide.
teacher too.
Yeah, he was my guide for my PhD and my master's project.
Yes, exactly. I saw that. And I was so happy to see because you have written that even now, if you have a problem, anything regarding, you go and consult him.
Yes,
So
very
that
much.
exactly shows the value of a teacher and how you pay regards to him, how you still remember him. So we all pay our regards to you for setting those feelings, those emotions on your official page. And as the page said, that she's a professor of organic chemistry. And in the Vinayak Gajanan Vaze College of Arts, Science and Commerce, because most of the pages on the internet they say VG Vaze College. So VG stands for Vinayak Ganesh. So and she's a product of IIT Mumbai, where from she did her PhD. So I and she also has a magazine. She runs a magazine which is known as Vaze Chemica. And there was an interesting post. She said 175 faces of chemistry. So my regards, and we're so happy to welcome you on this lecture organized by the Internal Quality Assurance Cell under the PURE by the Institute of Excellence, Madhav Science College. This is in accredited as A grade college by NAC in 2015, and it happens to be a DST FIST college too. And there are a lot of students and a lot of faculty members from different colleges who have joined us, ma'am. And they'll be more than happy to listen to you, your enlightened talk on the CMR structure elucidation tools, PMR, CMR structure elucidation tools. We have been teaching them on these topics in the college regularly based on their syllabus. But I'm sure that looking from your point of view and looking from your view, it will be a great time. So as the schedule goes, I think Dr. Brajesh Pare, sir,
Yes.
just a small words of welcome to all those who are here, Dr. Pare.
Okay, yeah, definitely. Thank you, Dr. Dipen Raghavanshi. And it's a formal welcome. So, Dr. Lakshmi Ravi Shankar, who is our guest for today, Madam, in the college we have a sale. We call it a pursuit for research excellence. So this program is being organized under the aegis of this pursuit for research excellence and the Department of Chemistry and Pharmaceutical Chemistry. And so on the very onset of the my welcome, the official welcome, I just welcome our principal, Dr. Arpan Bharadwaj of the college. Today's guest, Dr. Lakshmi Ravi Shankar from Vajay College, Mumbai. IQSC coordinator of the college, Dr. Kalpana Singh, Dr. Jeevan Singh Solanki, who is the coordinator of pharmaceutical chemistry, and my friend and my colleague, Dr. Dipen Singh Raghavanshi, and all my colleagues of the department, the revered departmental colleagues and participants across India. I'm very happy to see the various participants from Pune and Mumbai and from the southern state of India also. So I take this opportunity to welcome our esteemed guest for today, Professor Lakshmi Ravi Shankar, a very devoted, a very popular, and extremely popular teacher. And she has been quite innovative in her teaching. She's known to me for quite long time, because she's very active in various activities other than the classroom teaching. As Dr. Kalpana Singh will read out, that the brief, the introduction, where we'll just all come to know about her, the activities even outside the classroom. Madam, very humbly, I would say that our college is grade A, and it is a DST fees supported college. And I'm happy to inform you that our college is a leading college in Madhya Pradesh, and humbly I would say that we stand among the first 5 colleges of our state. As far as the Department of Chemistry is concerned, we have always been having our master's classes, MSc classes, and at the same time, we have always been a registered center for research. And a good number of faculty members from the Department of Chemistry are engaged in doing research. So I welcome you, ma'am, to this college, which is a quite old college, an established college, and at the same time, our city, although physically you are not with us at the moment, but it's a very pious, classical, and historical city on the banks of River Shipra. So I welcome you for this webinar, for this session, which is definitely going to be a very, very fruitful session. And students will definitely, not only the students, but this program has been meant for the early faculty teachers also, those who have been recently recruited for undergraduate teaching and all that. So I welcome you once again, madam. Thank you very much.
Thank you, sir.
So taking the mic now, I'm so thankful to you, Dr. Pare. And we are also proud that the faculty member, head of Department of Chemistry, is also the president of ICT, that is the Institute of, the
Thank you, sir. Thank you.
Indian Chemistry Department, ISCT. So I am so happy that, because there has been a galaxy of speakers that have joined our college in recent months. This COVID has brought this honor to our college, basically, because a large number of teachers who cannot travel to Ujjain and who cannot be physically present in our college have joined us in different platforms, in seminars, in webinars, and they have all come here to join us. So thank you so much, Dr. Pare. And now I request Dr. Kalpana Singh to give introduction, a formal introduction of our guest, Dr. Lakshmi Ravi Shankar. Please, Dr. Kalpana Singh, please.
Thank you. I'd just like to welcome Dr. Lakshmi Ravi Shankar on this virtual platform hosted by Government Mother Science PG College Ujjain. Before reading your brief profile, which I would just like to say 2 things. One is hats off to you, madam. I'm just overwhelmed by the CV, which I was just explaining. Whosoever was coming in my way, including my family members, I was just, मैं उनको पकड़ के बता रही थी. I was telling them that just look at the teacher that we have in chemistry right now. So such is I can say such is the brief profile of Dr. Lakshmi Ravi Shankar. Hats off to you, madam. You are an outstanding teacher. I can just say this by seeing your PowerPoint slides. You are just outstanding teacher, madam. Most welcome. Dr. Lakshmi Ravi Shankar is Dr. Lakshmi Ravi Shankar is a professor, Department of Chemistry, VT Vaze College of Arts, Science and Commerce, and in Mumbai. She has a teaching experience of 33 years in UG and 29 years in PG. She owes membership in many university positions: Board of Studies in Chemistry, Mumbai University; member Board of Studies in Chemistry, SIES College Autonomous Mumbai; member of Syllabus Committee for MSc, PhD integrated programs, BSc programs, different programs. She has been a member to all these programs. She has a membership in professional bodies like Indian Chemical Society, Chemical Research Society of India, Indian Association of Chemistry Teachers. She's a associate member of Royal Society of Chemistry UK since 2016, Executive Council, Royal Society of Chemistry, West India section. She has published many papers, but with this, She has many awards and achievements to her cap, and she has been selected for the 6 months UNESCO-sponsored Open Education Resource for a better world mentoring program in 2020. She developed a 4-week MOOCs course on pericyclic reactions, developed 12 YouTube videos on various topics of pericyclic reactions, and offered it on MOOCKit, a platform of IIT Kanpur. She has been awarded the Best Teacher Award in Chemistry by the Global Society for Basic and Applied Sciences, Thane, Mumbai, in association with NIST Academy of Management Studies, Dubai, in November 2019. She is selected for the 6 months UNESCO-sponsored Open Education Resource for a Better World Mentoring Program, January to June 2019. She developed an online course module on nucleophilic substitution reaction. She received the Inspirational Member Award from Royal Society of Chemistry UK in July 2018. She was the mentor of Indian team participating in the 50th International Chemistry Olympiad held at Czechoslovakia Republic from 20th July to 28th July 2018. The Indian team secured 2 gold and 2 silver medals in this event. She has been featured as one of the faces globally for the 175 Faces of Chemistry project of Royal Society of Chemistry, United Kingdom in April 2015 to commemorate their 175th anniversary. She was the first from India to be nominated for the same. She received the INSA Teacher Award 2013 from the Indian National Science Academy for motivating students to take up career in science. She received the Best Chemistry Teacher Award at national level for innovation in teaching from Tata Chemicals and Association of Chemistry Teachers in January 2012. She received the Chemical Research Society of India CRSI Best Teacher Award at first CRSI zonal meet held at National Chemical Laboratories, Pune during May 13 to 14, 2011. She won the second prize at the National Intercollegiate Competition on what steps should the chemical industry take to improve the quality of education and academic research in India, jointly organized by BASF India and ICT Matunga. She was head mentor of Indian team participating in 42nd International Chemistry Olympiad held at Japan from 19 July to 27 July 2010. Indian team secured 3 silver and 1 bronze in this event. She received the Best Teacher Award of Mumbai University for year 2015 for the year 2005-16 in recognition of contributions of knowledge. She received the Chemical Research Society India CRSI Best Teacher Award, and she was mentor of Indian team participating in 37th International Chemistry Olympiad held at Taiwan from 16th July to 24th July 2005. She has a research interest to open educational resources, technology for teaching and learning, chemistry education, green chemistry, solvent-free reactions, and multi-component reactions are a few to name among her research interests. She has done many projects too, including minor. She has guided students for PhD and MPhil, and she has published 24 papers in national and international journals. She has presented papers in several research conferences in India and visiting faculty for chemical technology for Institute of Chemical Technology, Mumbai for the BChem, Chemical Engineering and BTech program, Center for integrated MSc programs, and she has been actively involved in National Chemistry Olympiad programs, invited to be a reviewer of the National Program in Technology Enhanced Learning Program of IIT Bombay, organized several workshops, and initiated annual publication of in-house magazine Vaze Chemica in 2009. She is actively using ICT in classroom teaching via Google Classroom. She has developed PPTs with audio and sharing them as resources in Google Classroom. Hats off to you, ma'am. As I already said that, such are the credentials that anybody will want to listen to you. So I would not now be come in between you and your students. I would just add 1 or 2 things here. I request all the participants to please mute your mics for better learning experience. because we are here to learn. So please mute your mics, please mute your videos. Your chats has been disabled. So if you have to ask any question, you just raise your hands. We'll be taking these questions after the end of the madam's session, and there will be a break for 15 minutes in between the session. So please mute your mics, mute your audio and video, and just learn today. Thank you, ma'am. I welcome you, ma'am. Please come forward. The floor is yours.
Thank you so much, Dr. Kalpana. Am I audible?
Yeah, ma'am. Perfectly.
Thank you so much, Dr. Kalpana. Good evening, Dr. Bharadwaj, Dr. Pare, Dr. Raghuvanshi. I'm so happy that I have been able to, I've been invited on this virtual platform to share the topic which I feel is very close to any organic chemist, because this topic, I find that very often I find students find this topic difficult, and the most easiest thing that they can do when it is difficult is leave it as an optional topic. So very conveniently, they leave it as an optional topic. And then when they come to MSc for the MSc program, at the MSc level, when they have an entire paper on spectroscopy, they find it very, very difficult. So I will be discussing about not the entire spectroscopy, but I will be discussing about the two important proton magnetic resonance and carbon-13 magnetic resonance. And I will be talking about the applications of these in structure elucidation. Will not be going into the theoretical aspects as far as the instrumentation or the physics, the pulses, etc. I will not be covering those. Before I start, again, I thank the organizers for the kind words that have been spoken. Guest teaching is my passion, and I hope that I'm able to convince students that this is not a difficult topic and they should not keep it as an option. So today what I will be covering is the basics of spectroscopy, PMR, CMR, two-dimensional NMR, and problems. This is going to be quite an ambitious thing, but I'm hoping that I will be able to cover practically all of this in this 3 hours of session that I have been given today. So what is exactly the spectroscopy? Spectroscopy is nothing but, you see, we have infrared, you have ultraviolet, visible, and ultraviolet, visible, nuclear magnetic resonance spectroscopy. These spectroscopic techniques, if you see, they are all non-destructive. Now, what do we mean by non-destructive? It means that after recording the spectrum of IR, UV, or NMR, I can recover my sample back, so I do not lose my sample. And basically, these techniques involve the interaction of molecules with electromagnetic energy. So what is electromagnetic radiation? How do I remove this? I'm getting this. What is electromagnetic spectrum? This is my electromagnetic spectrum. You have the low energy radio waves on the extreme right. And as you go from right to left, it goes on, energy goes on increasing, and you have the high energy gamma rays here. So depending on what is the source of energy that I'm using, I could use the energy source from radio waves, which is what we'll be using when we are talking about nuclear magnetic resonance. You can use energy source from the infrared. You can also use the energy source from the UV visible. So each of these regions of the electromagnetic spectrum, when they fall on a molecule, the energy is absorbed and you get a transition taking place. And depending on what is the level or what is the energy of the source of light that is being bombarded on the molecule, different types of transitions take place and you get different information about the molecule. So basically, there is an energy absorption taking place, irrespective of whether it is ultraviolet, infrared, or nuclear magnetic resonance regions. The best fundamental process is the absorption of certain amount of energy. And what happens when the energy is absorbed? The energy is required. It is transition takes place from a state of a lower energy to a state of higher energy. And this is directly related to the frequency of electromagnetic radiation, which is responsible for the transition. So if this is my energy level at the start, light is absorbed, there is an absorption, and when the absorption takes place, it is going from here to here. Now, depending on what is this energy gap, if this energy gap is very, very high, then obviously you will require a region from the electromagnetic spectrum which is corresponding to a high energy. So probably you will require energy from the UV visible region. But if this energy gap is very low, then you will have this energy gap. If it is very low, like in the case of NMR, even the radio wave region is good enough to bring about this transition. So in a typical experiment, the molecules or atoms start at a lower energy and go to a higher energy level upon absorption of radiation of the appropriate wavelength. So we have seen you have UV, visible, IR, NMR, mass. So what information, each of this gives you some information about the molecule. So this is something like a jigsaw puzzle. You get some information from UV, you get some information from IR, you get some information from NMR, you get some information from mass. So all these put together will give you an idea about what was the puzzle, or what in this case is the structure of the organic compound. So from ultraviolet spectroscopy, you get an idea about what is the extent of conjugation in the molecule. If your molecule is conjugated, then there is going to be absorption in the UV light, and you will get information in the extent of conjugation. From the infrared spectroscopy, you get an idea about either the presence or absence of certain functional groups, because functional groups have got characteristic frequency of absorption in the IR. So if you see a particular region where the functional group should appear, if you get a peak, for example, carbonyl, you can be sure that the compound contains carbonyl. If you do not observe a peak in that region, you can also conclude that your compound does not contain a carbonyl functional group. Nuclear magnetic resonance spectroscopy gives you an idea about the carbon-hydrogen framework in the molecule. And mass spectrometry, which does not use the electromagnetic radiation, the principle in mass is different from here, in the sense, here you bombard the molecule with a high electron beam, as a result of which one electron from the molecule is knocked out, and you generate what is known as the molecular ion peak. And if this molecular ion peak is visible, you get an idea about the molecular weight of the compound. So today we are not going to touch upon these three. We will be concentrating only on the NMR. So what exactly is NMR? We all know it is a powerful analytical technique which is used to characterize organic molecules by identifying carbon-hydrogen frameworks. Two common types, your proton NMR, which is known as PMR, and you also have carbon-13 NMR, which is referred to as CMR. And the source of energy for both of them is my radio wave region, which is the lowest in energy in the electromagnetic radiation. And when this low energy radio waves interacts with the molecule, they can change the nuclear spins of some elements, including proton and carbon-13. So if I want my molecule to be interacting with the radio wave, obviously there has to be a nuclear spin associated with the molecule. So basically, what is nuclear spin? There are nuclei. Some of the nuclei of some atoms have a property called spin, and these nuclei behave as if they were spinning, and each spin active nucleus has a number of spins which are defined by its spin quantum number I. So let us see some of the nuclei. This is the spin quantum numbers of some of the common nuclei that you will encounter in organic chemistry. So you see here, proton, carbon-13 and 19 fluorine, they have got a spin quantum number of half. Whereas 12 carbon and 16 oxygen, which are the most abundant isotopes of carbon and oxygen respectively, you see that they are having a spin quantum number of 0, So these are not NMR active. So while you can study the NMR of this, and the number of spin states that the nuclei can adapt is given by 2i plus 1. So when it is a proton or carbon 13, 2 into half plus 1, it gives me 2. So this can have 2 spin states. Deuterium can have 3 spin states, and nitrogen also can have 3 spin states because the spin quantum number for nitrogen and deuterium is 1. So elements with either an odd mass or an odd atomic number have the property of nuclear spin, and these nuclei will be NMR active. So the concept of NMR, this is your bar magnet. Your spinning nucleus can also be considered as a bar magnet, behave like a bar magnet, where it creates a magnetic field as a result of the spinning, and the direction of the magnetic field is related to the direction of the spinning of the nucleus. Like I said, I will not be going too much into the theoretical part of the spinning and the physics part of it. We are more interested in how the application is going to be done. So this is my spinning nucleus. If you see, it has got a random orientation in the absence of an external field. When there is no field, the nucleus spins in any way which it wants, and you see that the direction of the spin is also random. But when I place this nucleus in an external field, what happens is this random orientation takes up either this orientation or this orientation, which means when you place it in an externally applied field, this spinning, the orientation, it is either parallel to the external field or it is anti-parallel to the external field. So if you recollect that energy transition that I mentioned, you have a before and you had an after. There was energy being absorbed, and from here it was going up. So in this case, what is happening is, this is the low energy state, this is the high energy state. So there is a transition from the low energy state to the high energy state, and this energy gap is very less, and that is why you need only energy from the radio wave region to bring about this transition. So the low energy parallel state has more nuclei aligned to it as compared to the high energy. This is known as the alpha spin state. This is the beta state. So there is a greater number of nuclei here. Transition, it goes here. Now this does not remain in this position. It comes back to the ground state, gives off the energy that is known as a relaxation. You can have spin-spin relaxation, you have spin lattice relaxation. We are not going into the details of that. So this is my parallel state, which is my ground state. This is the anti-parallel spin state, which is the excited state. So the nuclei aligned with the magnetic field, this is known as the alpha state. They are lower in energy than the nuclei aligned against the magnetic field, which is known as the beta state. And there is a greater percentage of nuclei present in the low energy alpha state. So when you subject it to an electromagnetic radiation, the alpha state gets excited to the beta state, and this is what you're seeing. So for a flipping to take place, now what is meant by flipping? Flipping is transition from the alpha to the beta. To take place, energy of photon must be equal to the energy difference of this spin state. So this is my ground state. This is the excited state, the energy gap. Now when your energy difference between the allowed spin states increases linearly with the applied field strength. So you have an externally applied magnetic field. As you go on increasing the strength of the magnetic field, you see that this energy gap also widens. So when you have it at 1.41 Tesla, the energy is around 0.0239 joules per mole. But as you go to 7.05 Tesla, you find that this energy gap has increased. So the energy needed to induce a flip will be different depending on what is the strength of the externally applied field. So This is your basic spectrometer, NMR spectrometer. The magnetic field strengths are generated on the z-axis. So obviously you will require strong, powerful magnets. So you have two powerful magnets. The sample is placed in the spectrometer. So you have your sample, which is placed here, which is in between both these magnets. And it is bombarded with a radio frequency at a constant pace along the x-axis. So you have the radio frequency input, which gives you the radio waves. When the external applied field establishes the correct intensity, energy is going to be absorbed. Resonance occurs as the nuclei of the sample absorb the supplied radio frequency. And this resonance causes the nuclei to absorb a small current of energy and electricity, which is noted by the receiver coil. You have a receiver coil surrounding the sample, and that spectrometer amplifies the current from the receiver into a display of signals, which you know as the NMR spectrum. So this is basically the setup inside the NMR spectrometer. A powerful magnets on either side of the sample tube, and there is a radio frequency coil to provide the necessary radio waves. You have the input and you have the output. So this is the, if you have, many of you might have seen the spectrometer in your department or in some industries that you would have visited. This is the NMR spectrometer. Inside this, you have the sample tube is placed in what is known as a probe. So the sample tube is a long, thin glass tube, and you place your sample dissolved in a suitable solvent. Please remember, your solvent should not contain any proton, because if it contains proton, obviously you are going to get a signal for that also in the spectrum, and which would interfere with the spectrum of your compound. So this sample is placed in the probe, and this is actually rotated inside the spectrometer. Why is it rotated? If it is not rotated, all the molecules of the sample will not feel the uniform magnetic field. The ones which are closer to the end of the tube, which are closer to the magnet, would feel greater field than the one which is within the center of the sample tube. So that is why you rotate this sample tube or the probe in which you place the sample tube, so that there is a homogeneous magnetic field felt by all the molecules in the sample. So this is placed here. You also have the magnet within this, the radio frequency, all whatever I showed in the previous slide is there inside this, and this is where you have the spectrum that you will see when it comes out as the output. Now, there are 4 features when one looks for in a PMR. And if you are able to understand these 4 features and figure out what is the information that you get from each one of this, you can combine all these features and arrive at the possible structure for your compound. The first is the number of signals. Look at the number of signals, and what information does it give you? It gives you the number of signals, tells you how many different kinds of protons are present in your molecule. The position of the signals tells you what is the electronic environment about the proton, whether it is shielded or it is de-shielded. The intensity of the signal tells you how many protons of each type. For example, I've got 4 signals. From the intensity, I know signal number 1 is due to 3 protons, signal number 2 is due to 1 proton, so on and so forth. And the splitting of the signal tells you what is the number of protons on the neighboring atoms. So we will be seeing each one of them. Like I said, for some students, this may be trivial, but this is very, very important that one is sure of these concepts, because this forms the basis of the NMR or the PMR spectrum. So students should understand this before they try to solve more complex problems. So this is how an NMR PMR spectrum would look like. You have each signal will contain essential information which tells you about the integral, the multiplicity, and the chemical shift. So if you see these curves here, these are the integration curves, which tells you If you find the area under these curves or you measure the height of these curves, you will know what is the relative ratio of the protons responsible for this signal, responsible for this signal, responsible for this signal. For example, it is already shown this signal is for 3 protons. This signal is also for 3 protons. If you measure the height from here to here, it is going to be the same as from here to here. So these are for 3 protons. This is for 2 protons, and this is corresponding to 1 proton. So that is about the integral. If you see the scale below, you have 0, 1, 2, 3. This is the position of the signals, which we refer to as chemical shift, and we shall see that shortly. And this tells you, gives you the information about the chemical environment of each proton. And if you see these signals here, it is not a single peak. You're able to see 4 peaks here, and this is referred to as the multiplicity, and that is a reflection on the number of non-equivalent protons located on the adjacent carbons. So you have the integral, you have the number of signals, you have the multiplicity, and you have the chemical shift. So this is giving me 4 signals. That means this molecule C4H9Br has got 4 types of hydrogens present in it. Now, since it is 3 protons, so obviously this is CH3, so it has 1 CH3, it has another CH3 which is different from this, it has a CH2, and it has a CH. Okay, now this multiplicity we will be seeing shortly what it implies, but the number of signals gives you an idea about how many different types of protons are present. The position tells you what is the chemical environment, the electronic environment. The multiplicity tells you what is the nature of the neighboring protons, and the integration tells you how many protons of each type are present in this molecule. So let us see how to decide what will be the number of signals. So the number of NMR signals equals the number of different types of protons in a compound. So how do you determine the number of different types of protons? One way is if you are able to visually see and understand, fine. For example, this is dimethyl ether. This methyl is attached to oxygen. This methyl is also attached to oxygen. So all these hydrogens are equivalent. So this will give me only 1 signal in the NMR spectrum. Compare this with ethyl chloride. This is a primary carbon. This is also a primary carbon, but here this is attached to a Cl, whereas this methyl was attached to another carbon. So the environment is not the same here. So these 2 protons are not equivalent. So I will get 2 signals, one for this as well as one for this. So I'll get 2 signals. Now come to this. Here you have ethyl methyl ether. So this methyl is different from this methyl. You can say that this is attached to oxygen, this is attached to carbon, so the environment is not the same. So that is why these 2 methyls are different, and obviously this is going to be different from the CH2, so I'm going to get 3 signals. One way in figuring out whether a set of protons are equivalent or not, replace the atom proton by X. If you get the same product, then all those protons which on replacement gives you the same product will form one set of equivalent protons. Let us take vinylic systems. So look at this 1,1-dichloroethylene. Now if you see here, both these hydrogens are cis to Cl. So this is again one equivalent set. So I will get only 1 signal corresponding to this. But if I replace one of the chloro with a bromo, now you see that this is cis to Cl, this is cis to Br. So they are not having a common environment. The chemical environment is different. So I'll get 1 signal for this and 1 signal for this. If you look at this chloroethylene, very often students say that this will give me 2 signals, 1 for this and 1 for these 2 CH2 protons. But that is not the case, because if you write it like this, what you see is that this is cis to Cl, whereas this is trans to Cl. So they are not in the same chemical environment, and hence you will get 1 signal for this, 1 signal for this, and this carbon proton is different from both of them. So this will give rise to 3 proton signals in the PMR. Now you must have heard of enantiotopic and diastereotopic. faces when you talked of stereochemistry. Similarly, here you have enantiotopic and diastereotopic protons. So let us again revisit this ethyl bromide. We know that this methyl is going to be different from these two methylene protons. So this will, ideally you may say that we saw in the previous slide, this will give me two peaks, one for this and one for this. But are these two protons really stereochemically, are they different? How do you decide that? If I replace HA by Z, Z could be any group. What do you get? You get this structure. And if I replace HB by Z, you get this structure. What is the relationship between these two? They are a pair of enantiomers. And you know that enantiomers have the same chemical and physical properties in a symmetrical environment. So as long as you are not using any chiral solvent, your NMR environment is going to be symmetrical. So the NMR instrument cannot distinguish between these two isomers, enantiomers, and you will end up with only one peak for both these protons, although they are enantiotopic. But look at this R2 chlorobutane, where the stereochemistry of this chiral carbon is already fixed. Now let us see what happens if whether I will get two signals for these CH2 protons or will I get only one signal for this. Do the same exercise. Replace HA by Z, you will get this. Replace HB by Z, you will get this. Now what is the relationship between these two? They are a pair of diastereomers because this chiral center configuration remains the same. You have only changed the configuration of the other chiral centers. So they are a pair of diastereomers, and we say that these two protons are diastereotopic. And you know that diastereomers have different chemical and physical properties even in a symmetrical environment. So the NMR will be able to distinguish between these two protons and give separate signals for HA and separate signal for HB. So this molecule will actually give me 1, 2, 3, 4, 5 signals in the NMR spectrum because there are 5 different types of protons present in this molecule. We talked about the intensities of the signals. So let us consider this molecule, tertiary butyl methyl ether. So if you see, you have two signals. This signal is due to 9 protons and this signal is due to 3 protons. So if you see this integration curve, you measure the height of this and measure the height of this, and you will find that this height is in the ratio of 3:1. You have 9 protons and 3 protons. The protons are in the ratio of 9:3 or 3:1. So similarly here, this integration is in the ratio of 3:1. So it's possible for you to find out, even if you don't know what is the, you know what is the molecular formula, but you have to find out what is the structure. You can use the integration curves to find out each signal is due to responsible or how many protons are responsible for each of the signals. Next, we come to the position of these signals because that gives you a lot of information about the molecule. So assume that whether I take cyclohexane or I take acetophenone or I take any molecule, if all the protons in that molecule were to feel the same externally applied field, then I'm going to get one peak for all the molecules that are present on planet Earth. You will not get different proton signals. You will get only one peak for all of them. And that is not going to help us in any way. So if all protons absorb the same amount of energy, you will not get much information and they are not going to be useful as well. But what happens is, you know that protons are surrounded by electrons, and depending on what is the electron density around the proton, it could be either having a greater electron density, in which case we say that it can be shielded by the electron cloud, or it can be having a lesser electron density. So protons are surrounded by electrons which can shield them from the external field, and the extent of shielding will vary depending on what is the chemical environment of the proton. And that is what is responsible for difference in the absorption of the, or difference in the extent to which the externally applied field is felt by individual protons, and you get different peaks for them. In addition to that, you also have induced magnetic field which are generated by circulating by the pi electrons. Sigma electrons also generate induced magnetic field by circulation, but the effect or extent of the induced magnetic field by the sigma electrons is much, much less than that which is caused by circulation of the pi electrons. So shielding can occur by presence of elements, atoms which can be electron releasing. It can also be caused by circulation of pi electrons, creating an induced magnetic field which opposes the externally applied field. So what I'm trying to tell you is, let us assume that this is the proton. I'm studying this under NMR. So I have a group Z attached here. Now Z is going to release electrons. What is going to happen? It is going to increase the electron density around this proton. So if there is a greater electron density around this proton, when I apply an external field, obviously the electron cloud is going to protect this proton from the external field. And we say that the proton is shielded. But suppose you have a group which is electron withdrawing, like say a nitro group, which pulls electrons towards itself. So what is going to happen? The electron cloud is more towards the Z. So the hydrogen proton is as good as not having an electron cloud around it. So in which case, it is going to feel the full effect of the externally applied field, or the proton is de-shielded because of the effect of the electron withdrawing group. So if Z is electron withdrawing, you have a lesser electron density around the proton, and we say it is de-shielded. If Z is electron releasing, you have a greater electron density around the proton, and we say that it is shielded. So shielding and de-shielding, one of the factors is the presence or absence of an electronegative atom. So let us see if we are able to illustrate it with this diagram. This is my proton, which is not surrounded by any electrons. And I'm placing it in a 60 megahertz instrument, NMR spectrometer. And the field strength that I'm applying is 14,092 Gauss. Now, since there is no electron cloud, this proton is going to feel the entire effect of the 14,092 Gauss, or we say this is a naked proton, which will feel the full impact of this. But suppose that this proton is surrounded by an electron cloud. So what is going to happen? The magnetic field is going to be there, but this electron sheath is going to be a sort of hindrance. It is something like the bodyguard. Somebody wants to attack you, but you have a string of bodyguards. They are going to prevent the attack of the thieves towards you. They will be the first line of control. They will be protecting you from the attackers. But suppose you had only one bodyguard, then obviously, and there are 10 people coming to attack you, then obviously you are exposed to all 10 of them. It's similar to that. So if you have an electron cloud here, that is going to act as a protective shield, and it is not going to allow the proton to feel the full impact of the magnetic field strength. So what happens? The field strength which is felt by the proton is actually less than what is you have applied. So let us say it is 14,091.7. Now, if I want this proton to feel this strength, what I should do, I have to apply a stronger applied field strength, which will compensate for the shielding. It is not much, it is only 0.3 Gauss, but that can create a lot of information can be derived by just changing the magnetic field strength. You are applying a greater field strength to overcome the effect of the shielding caused by the electron cloud. I hope it is clear to all of you. So we have what is known as a standard, we'll come to that, but a shielded nuclei is one which has a greater electron density. They sense a smaller effective magnetic field. If you see here, this was shielded, so the effective field felt by this proton is going to be less than what was actually applied. So these protons sense a smaller effective magnetic field, so come into resonance at a lower frequency. A de-shielded nuclei will sense a larger effective, so that means the proton is more exposed to the externally applied field. They come into resonance at a higher frequency. So this is your NMR, please remember. Shifting to the right, we refer to it as upfield. Shifting to the left, we refer to it as downfield. This refers to a low external field. This is to a high external applied field, and the frequency increases as you go from right to left. So let us take the example of methanol. Now these three protons, if you see, they are more shielded. The oxygen is there, but the oxygen is not directly attached to the proton. It is attached to the carbon, whereas this proton is directly attached to the oxygen. So this is less shielded, and hence it absorbs at a lower field. It will appear downfield. Whereas these three protons are, compared to this, they are upfield, and hence you see that you see this signal for the methyl, and this signal is for the hydrogen, which is attached to the electronegative atom. So now we come to the term the chemical shift. So how does one define the chemical shift? It is the difference in frequency. Please remember the chemical shift. The actual unit for chemical shift is actually hertz. It is the difference in frequency between the sample and the standard. Like I said, if I'm running 100 meters race, I have to know what is my starting point from where I can measure 100 meters and say that this is the distance that I have traveled. Similarly, when you talk of chemical shift, when we say that a proton signal comes at this point, I should know from where I'm going to measure that. And for that, you need a standard. And the standard used is TMS, or tetramethylsilane. Very often in Viva, when we ask the students what does TMS stand for, the prompt answer is trimethylsilane. Please note it is not trimethylsilane, it is tetramethylsilane. Now, why do you use this as a standard? This is used, it has got several reasons. One is it is very volatile. I think it is around 29 degrees centigrade or so. So immediately after you have recorded the spectrum, you can easily remove it. It is inert. It does not react with your it does not react with the compounds. And since there are 4 methyl groups attached to the silicon, all of them are equivalent, and you get only a single peak, which is very, very intense for 12 protons. All the proton signals are downfield because silicon is more electropositive than carbon. So the methyl protons of TMS are going to be highly shielded, and most of the other protons are de-shielded with respect to TMS. Now, when you express the chemical shift in hertz, you have to specify what is the operating frequency of the instrument. For example, if I'm running the spectrum of a sample in, say, a 60 megahertz instrument, and I see that my peak is coming at 60 hertz. If I run the spectrum of the same sample in a 500 megahertz instrument, I will find that now the signal is appearing at 500 hertz. So that means this chemical shift is a function of the operating frequency of the instrument. So very often, if nowadays, of course, nobody reports the chemical shift in hertz, very often you use the ppm values, which delta scale, which we'll see in the next slide. But if you are expressing the chemical shift in hertz, you have to specify what is the operating frequency of the instrument. And that is very important. That's why it is highlighted that when the chemical shift is expressed in hertz, it is necessary to mention the operating frequency of the instrument. So every time it is difficult to go on mentioning. Suppose I have done research, I have identified some compound, and I have taken its spectrum in, say, 100 megahertz instrument, and I try to compare the data from the literature, and I find that somebody else has done it using a 300 megahertz instrument. My values of chemical shift would not match with the values of the chemical shift reported in the literature. So hence, very often there is a confusion and people can get confused. So better to convert the chemical shift in hertz to a dimensionless quantity, which we call as delta. And how do you bring about this conversion? By taking the ratio of the chemical shift in hertz and divide it by the operating frequency of the instrument in megahertz. So in the previous slide, if you see, we said that it was 60 hertz and my instrument was operating at 60 megahertz. So I divide 60 by 60, you get the value equal to 1. If I take it in a 500 megahertz instrument, I find that the chemical shift is 500 hertz. So 500 divided by 500, it again comes out to be 1. So when you do the chemical shift is expressed in delta scale in ppm, you find that it is independent of the operating frequency of the instrument. You will get the same value irrespective of whether you have measured it on a 60 megahertz, 100 megahertz, 300 megahertz, or even 1000 megahertz instrument. So basically, people now use the delta scale to express the chemical shift. But bear in mind, chemical shift unit is actually hertz. And when you express it in hertz, you have to specify what is the operating frequency of the instrument. So what are the factors which affect the chemical shift? There are 4 major factors which account for the resonance positions. We are talking about the ppm scale now. One is de-shielding by the electronegative atoms. So which means basically it depends on what is the inductive effect of the electronegative groups that are present. Second is the S character or the nature of the hybridization of the atom to which the proton is attached. Magnetic anisotropic effect. These are the induced magnetic fields which are generated by circulation of the pi electrons in the molecule. And the last is hydrogen bonding. So these 4 factors affect the chemical shift, and we shall quickly go through each one of them. So if you have an electronegative atom, so you have methyl fluoride on one end, you have TMS on the other end, and in between you have methanol, methyl chloride, methyl bromide. Fluorine is the most electronegative. So if you see here, the pull of electrons is going to be more towards the fluorine. So the hydrogens are as good as not having the electron pair, or we say that they are going to be de-shielded. And that is reflected in the chemical shift, which appears at 4.26 ppm. If I go to chloromethane, chlorine is not so electronegative. So you see that it is relative to this has gone an upfield shift. Methyl iodide, iodine is the least electronegative amongst the halides. So you see that this has gone still further upfield and appears at 2.16 ppm. So based on the electronegativity, it is possible for us to predict or to assign the order of chemical shift for these halide substituted compounds. So de-shielding increases with the electronegativity of the atom X. It is also cumulative. So if I have more than one halogen, you have methyl chloride, which is at 3.05. When you have 2 chlorines, you see there is a de-shielding, further de-shielding. Chloroform, you see there is a still further de-shielding. So the effect increases with the greater numbers of electronegative atoms. Just as inductive effect decreases with the distance, you will find that the chemical shift also, if the electronegative atom is away from the proton, see here it is directly attached to the carbon. So these protons are going to feel the maximum effect. You see they are de-shielded. 1 carbon away, they are more upfield. 2 carbons away, they go still more upfield. So the effect decreases with the increasing distance from the electronegative atom, and almost from the 4th bond, you will see that this effect is not going to be there, and it is not reflected in the NMR chemical shift. Hybridization and chemical shift. let's take a quick look at how the hybridization is going to affect the chemical shift. As the S character of the carbon atom increases, we all know that when the S character increases, the electronic cloud is held more closer to the carbon, and hence, or we say that it is more electronegative. So around the proton, the electron density is going to be reduced, as a result of which they are going to be de-shielded. And thus the chemical shift will increase, or it will be shifted downfield. So if I take sp3, a hydrogen attached to an sp3 carbon, a hydrogen attached to an sp2 carbon, and a hydrogen attached to an sp carbon, this is going to have the maximum percent S character. So based on this, this should be the most electronegative, or this proton should be the most de-shielded. So one would expect this comes around, say, 0.9. This should be more de-shielded, and this should be still more de-shielded, somewhere around 7. If it was only the S character increasing and the electronegativity effect. But what we observe is that the sp hydrogen appears at 2 to 3 ppm, which means compared to this, this is actually going upfield, or it is going to be shielded. So the order of the chemical shifts is an sp2 hydrogen attached to an sp2 carbon is having a greater chemical shift than an sp carbon, a hydrogen, which is having a greater chemical shift than an sp3. So that means besides the electronegativity, because if it was only the electronegativity, you should have observed this trend. But what is observed is this. So because this is the trend observed, that means it is not only the electronegativity or the percent S character which is playing a role, there is something else also which is playing a role, and that is what is referred to as the magnetic anisotropic effect. So this suggests that other factors than the sp character of carbon might be affecting the chemical shift in this case, and this discrepancy is explained by what we call as the magnetic anisotropic effect. So what is the magnetic anisotropic effect? Anisotropy means a property which changes with direction. Isotropy is a property which does not change with direction, and this arises due to the presence of pi bonds. So if you have a nearby pi bond or a pi system, it greatly affects the chemical shift, because these pi electrons circulate and they generate induced magnetic fields, which, depending on whether they are reinforcing or opposing the external field, you will have either shielding or de-shielding situation. So magnetic anisotropy is a property which changes with the direction. When a molecule containing pi electrons is placed in an external magnetic field, then these pi electrons circulate and generate an induced magnetic field which opposes the external field. And if at the site of the proton, the induced magnetic field opposes the external field, we refer to it as a shielding situation. And if it is reinforcing the externally applied field, then it is referred to as a de-shielding situation. Like I said earlier, sigma electrons can also circulate and generate induced magnetic field, but their effect is very less and they are not significant. So normally they are not considered. So let us take the vinyl protons. The vinyl protons, if you see, they normally come around 5 to 6 ppm. Okay, so if this is the direction of the externally applied field, and this is the orientation of the molecule, this is my pi cloud, and you see that these pi electrons are going to circulate and they are going to generate an induced magnetic field which is going to oppose the external field. But see the direction at the site of the proton. Where is my proton? My protons are here. At the site of the proton, what is the direction of the induced field? It is parallel to the external field. So we refer to this as the de-shielding zone. So the induced field reinforces the external field at the site of the proton, and hence it is de-shielded. If I had a substituent here and some proton comes in this region is the shielding zone, then that proton would be highly shielded and it would be going upfield, moving more closer to the TMS. Now let us see the case for acetylenic protons. The acetylenic protons now appear at 2.3 to 2.5. So if you place the acetylenic proton like this, you see that at the site of proton, this is the circulation, there is generation of induced magnetic field. At the site of the proton, my proton is here, not here. This is the de-shielding zone. The proton is here, and at the site of the proton, it is going to be opposing the external field, or it is going to be a shielding situation. Now, this question has always bothered me. Suppose I have placed here the acetylene molecule with its axis parallel to the external field. What happens if I place the acetylenic molecule with it perpendicular to the external field like it was this? So I place the acetylene like this, in which case the protons should have been de-shielded. But what, to be honest, I have really not got a very satisfactory answer for this. But what in general I have been told is that these are all experimental observations. So several studies on several acetylenic molecules have been done. And in all the cases, it has been found to be having in this region. And that can be explained only if you consider the acetylenic molecule with its axis parallel to the externally applied field, such that at the site of the proton, the induced magnetic field is opposing the external field, as a result of which these protons are shielded, and hence they are undergoing an upfield shift. If you consider the aromatic protons, they are all having pi electrons, and one would expect that, like the olefin, one could expect the aromatic protons also to be somewhere around 5 to 6, but they are highly de-shielded. In fact, if you do not observe a peak in this region of say 6.5 to 8.5, then you can be sure that your compound is not having any aromatic protons. So here again, you have a pi electron cloud. These pi electrons will circulate under the influence of the external field. And when they circulate, they will generate an induced magnetic field. And now if you see here, where are my protons? Here my proton is there. There's going to be a proton here. There's a proton here. And there's going to be a proton here. So at the site of the proton, if you see, the direction of the induced magnetic field is parallel to the external field. It is reinforcing the external field. So these protons are de-shielded, and that is why they are going downfield. Now, this is the de-shielding zone, which is my shielding zone. This is my shielding zone. So suppose you have a substituent here. Let us say you have a long chain substituent here. And if those protons, any of those protons fall in this region, then, then the proton is going to be highly shielded, because it is going to fall in the shielding zone of, this is known as the ring current effect, and it is going to fall in the shielding zone. So any proton which falls in this region is going to be shielded because of the ring current effect of the aromatic pi bonds. But since the protons of the aromatic ring are outside that, they are in the de-shielding zone, you find that they are going, a de-shielding is observed, and it appears at 7 to 8 ppm. A last example is of the aldehyde. If it was only the carbonyl electronegativity, one cannot anticipate a value of 9 to 10 for the aldehyde proton. So in addition to the minus I effect of the carbonyl, there is also the anisotropic effect of the carbonyl pi bonds rotating, generating an induced magnetic field, which here again at the site of the proton, it is reinforcing the external field, and hence this is adding additional de-shielding. There is some de-shielding because of this carbonyl. Further de-shielding is being caused because of this induced magnetic field, which is reinforcing the external field at the site of the proton. So if you do not have any signal in this region, you can be sure that your compound does not contain an aldehyde group. So to summarize the chemical shifts, the aromatics, they are highly de-shielded, come to 6.5 to 8 depending on the substituents. And vinylic proton is again de-shielded, appears around 4.5 to 6 ppm, An acetylenic proton is shielded. It appears somewhere around 2.5 ppm. The last part was factor which affects the chemical shift is hydrogen bonding. So what is required for hydrogen bonding? Obviously, you will require a hydrogen, but not any hydrogen. The hydrogen has to be attached to an electronegative atom, and you should also have another electronegative atom in the vicinity. So if you take an alcohol, you can have intermolecular hydrogen bonding. So what happens because of hydrogen bonding? Now you see here, this hydrogen bonded, it is bonded on both sides, it is being pulled. So this lengthens the OH bond, as a result of which the electron density around this is going to reduce. And when the electron density around this proton is reduced, it is going to undergo de-shielding, or it will undergo a downfield shift. So alcohols can vary in chemical shift if it is not hydrogen bonded. That means it is free. It will come somewhere around 0.5 ppm for a free OH. But if you have hydrogen bonding, it can go up till 5 ppm. Now, again, this depends on what is the nature. If you recollect in the previous one slide of methanol, we saw that it was coming around 3. So that again depends on what is the frequency of your operating frequency of the instrument. And the same time, of course, when you take it in ppm, that is not going to change, but depends on what are the other groups present in the alcohol. But this would be, I wouldn't say it is around 0.5, because oxygen's electronegativity will be playing a role. It will be shifting it downfield. But when it is hydrogen bonding, it can go still further downfield. How do you identify a peak, whether it is due to a hydroxyl or an NH? Normally, one is these peaks are very broad, and if you add D2O to the sample, if they are if it is due to a OH or an NH, on addition of D2O, you will find that these peaks will disappear on shaking with D2O, and that is because there is an exchange of ROH with D2O to give you ROD, and that will not give you the peak for ROH in the NMR spectrum. You will get an HOD peak, but that comes at a standard value, if I'm not mistaken, around 7 point something, and that you can identify. I'm sorry, that is around, I think, 4 point something, which you can identify. So using the D2O exchangeable, you add D2O, from that you can figure out if the peak disappears on addition of D2O, a broad peak disappears, then you can be sure that the compound contains either a hydroxyl group or an NH group, because these are exchangeable protons. So this is the chemical shift. So you have the TMS here. Your sp3 carbons normally are 1 to 1.5. Then you have the acetylenic, and you have the methyl vinylic type of protons. You have groups which are attached to electronegative atoms. Then you have the vinylic, aromatic, the aldehydic, and the acidic proton. So the shielded protons absorb at lower chemical shift, that is to the right. De-shielded protons absorb at higher chemical shift to the left. Now, very often students are not able to remember all these chemical shift values. In fact, you don't have to remember all of them. If you remember some of them, and you can have a simple guide on how to predict the chemical shift. What you should remember is the value for a CH3 group, which is attached to another carbon, that normally comes around 0.9 ppm. You add 0.4 ppm, so 1.3 ppm is for a CH2 group. You add another 0.4 ppm, you get the value for a CH group. So 0.9, if you remember, and you remember 0.4, increment of 0.4 will give me the chemical shift for a CH2, which is attached to carbon. Increment of another 0.4 will give me the chemical shift for a methyl. Now, when you replace each hydrogen atom in CH3 by a carbon, carbon being more electronegative than hydrogen, therefore shields less effectively, and that is why you see a slight downfield shift. Okay, so now if your CH3 is attached to an oxygen or a halogen or a nitro, you will add 2 ppm to this. So I know the base value of 0.9 ppm. Suppose I have OCH3. All I have to do is add 2 ppm to this. So approximately it will come to 2.9 ppm. If I have CH2 which is attached to OCH3, then this, or to an oxygen, then this CH2 will have to add 2 to this, so this becomes 3.3. If I have a CH which is attached to an oxygen or a nitro or a halogen, then it becomes 2 plus 1.7, it becomes 3.7. Similarly, if I have an alcohol or a CH3 attached, so these are values to be added to 0.9 for CH3, 1.3 for CH2, and 1.7 for CH. If it is CH3OH, you will add 2.9, it will be. If it is CH2OH, it will be 2.9. Similarly, if it is an aryl ether, you have to add 2.5 to 9. If it is an ester, you will have to add 3. So if you remember these incremental values and you remember these 3 values, you will be in a position to predict the chemical shift for different protons. For example, this is the molecule CH3CO, CH2, COO, CH3. Can I predict what will be the chemical shift for this CH3CO? So methyl I know is 0.1, and when it is attached to a carbonyl, you see that this is attached to a carbonyl. I have to give an increment of 1 ppm. So 0.9 plus 1, this comes to, calculated is 1.9, observed is around 2.1 ppm. Similarly, if you see this CH2, the base value you will start with is 1.3. On one side, you have to add 1 ppm because of the effect of the carbonyl. On the other side, this is an ester. And if you see an ester, this is also C double bond O of the carbonyl. So I'll have to add 2 times. So it comes to 3.3. So this is also 3.3. What about this methyl? It has to be 0.9. And this methyl, please see the difference. This is CH3 or CH2 attached to a carbonyl, whereas this is a CH3 or a CH2 attached to the oxygen of the ester functionality. So now here I have to add 3. So this comes to 3.9, and what is experimentally observed is 3.7. So just by remembering a few base values and the increments, it is possible for you to predict what is the chemical shift. So suppose you were asked to predict the value for CH2 in this molecule. So CH2 is attached to phenyl on one side and COCH3 on the other side. So for phenyl, it is 1.5. For CO it is 1. So it comes out to be 3.8, and the experimentally observed is also 3.8. Again, electronic effects. If I have an electron withdrawing group, you can see that because of the delocalization, this carbon becomes electron deficient. If it is electron deficient, that means it is deshielded, and you are going to see that there is going to be a downfield shift, which is reflected in 8.48. Here it is 8.1 because this is not as effective in delocalization as this. So depending on the delocalization, if there is a positive charge generated, then it is going to be de-shielded. Look at this. Here you have both plus M, you have resonance, positive resonance because of donation, and you also have a minus I because of electron withdrawal. Now, if you see here, the electronegativity of iodine is much less than that of fluorine. Okay, so here if you see this, there is a greater electron, the donation here, this greater electron withdrawal is there, but at the same time, you're also having release of electrons. Remember, the orbitals in which this lone pair of electron is not in the 2p. So electronegativity is important if size is important for 2p orbital overlaps efficiently. So you see here that here the orbital overlap is not going to be so efficient because these are all in higher orbitals as compared to the 2p here. Now this is in the 2p, this can overlap. This is also having minus I effect, a very strong minus I effect. So both these together, that's why this comes out to be 7 ppm, whereas here this is 7.24, slightly more deshielded. This is still more deshielded, and this is still more deshielded. So here now again you have electron donating groups. When you donate electrons, you're going to increase the electron density on this carbon. And when you increase the electron density on this carbon, this proton is obviously going to be more shielded. And if it is more shielded, it is going to go an upward shift or an upfield shift. And that is what you are seeing, that when you have oxygen which donates electrons, you see this is 6.8, this is 6.9. For nitrogen, it comes out to be 6.35. So there is a balance between electron releasing as well as electron withdrawing. Similarly, if you take benzene, they are all 7.27. Vinylic is 5.68. But suppose you have this conjugated system where you have delocalization possible. So this becomes electron deficient. And if you compare this with this, here there is an electron release. So there is a greater electron density on this carbon, which is reflected in the chemical shift of this proton, which is going upfield. Whereas here, there is a greater electron reduction, or there's a positive charge here, as a result of which this is de-shielded. So similarly, electron deficient nitroalkene pulls the electron towards itself. So this has got a minus, 7.31, that is, it is de-shielded. If you talk of a acylyl ether, this can release electrons, greater electron density, that's why it's an upfield shift. So remember, when you can release electrons, if it are generating something like a carbon ion, then the proton attached to that carbon will undergo an upfield shift. But if it is electron withdrawal by resonance, then that proton, which is getting a positive charge, will be shifted downfield. If you see DMF, one would think that both these methyls are going to be having the same chemical shift, but you actually see two signals, and that is because of the delocalization. You get a structure like this, and once this is formed, you see now there is no longer free rotation possible about this. So these two methyls are not in the same chemical environment, as a result of which you're getting two signals due to restricted rotation about the NCO bond. Now we come to the last part of the PMR, and that is the spin coupling. So you have in spin coupling, you will be seeing the multiplets, you'll be seeing spin systems, simple first order and complex second order. So why do we get these coupling? It is basically because of the interaction of the nearby protons, which give rise to multiple peaks. So spin-spin splitting is basically due to the presence of non-equivalent protons on adjacent carbons, which have magnetic fields which at any given time could be aligned with or oppose the external field. And this magnetic coupling causes the proton to absorb slightly downfield when the external field is reinforced, and slightly upfield when the external field is opposed. And since all possibilities exist, the signal is split. It's a through bond effect. The coupling constant is always measured in hertz, and it is proportional to the effectiveness of the coupling, represented by J. If two atoms, protons A and B, are coupled, then we represent it as JAB, and the coupling constant rarely exceeds 20 hertz. One thing you have to remember is the coupling constant is independent of the operating frequency of the instrument. If you recollect, when we talked of chemical shift, I said if you are expressing the chemical shift in hertz, you have to specify what is the operating frequency of the instrument. But if I record the chemical shift, the coupling constant, I find it is 20 hertz in a 60 megahertz instrument. If I run the same sample in a 500 megahertz, I will still find that the coupling constant is going to be the same. That means the chemical shift when you express in delta, and the coupling constant when you express in hertz, these two are independent of the operating frequency of the instrument. This is very important. Chemical shift expressed in delta. The multiplicity, very often, yes, this is very, very important. Very often when you ask students, why do you get a quartet, or what is the cause for a quartet? And the answer I get very often is it is a CH3 signal, and the quartet is because there are 3 protons. So if you have a CH3, CH2, the CH3 ethyl group, the CH3 gives me a triplet. Now, why do you get a triplet? Very often the students give me an answer because it is attached to 3 protons. Please note, the number of lines observed in the NMR signal of a group of protons is not related to the number of protons in that group. Very often, I'm sure many teachers will agree with me, When you ask students simple question in the Viva, in the ethyl, you get a triplet and you get a quartet. The triplet is due to the methyl. Why do you get a triplet for the methyl? And the standard answer which we get is methyl has got 3 protons attached to the carbon, and that is why it gives me a triplet, which is not the case. The multiplicity of lines is related to the number of protons in the neighboring groups. It is just like you have neighbors, how many are there next door? And it is given by n plus 1, but please remember this is only for a first order spectrum, and we shall see shortly what is meant by a first order spectrum. So spin-spin splitting, please remember equivalent protons do not split each other. Protons bonded to the same carbon will split if they are non-equivalent. Protons on adjacent carbons normally will split each other. Protons which are separated by 4 or more bonds will not split each other. You may have long range couplings, which is known as W coupling. We shall see shortly that. So let us quickly see 1,1,2 tribromoethane. Now you see here that this is giving me a triplet and this is giving me a doublet. These 2 protons are obviously, this proton is going to be more de-shielded because of the presence of the 2 BRs. So this proton is my triplet and this is my doublet. So why is it that I'm getting this and not single peaks? So with no adjacent hydrogen, the absorbing hydrogens feel only one magnetic field. But suppose there is a hydrogen on the adjacent carbon, what happens? That hydrogen also can undergo spinning and generates a field. So at any given time, that induced field on that adjacent proton could be parallel to the external field or anti-parallel to the external field. So this proton which feels this effect will be de-shielded slightly. The protons which feel this effect will be shielded slightly. So that is why you get 2 signals, and which is seen here. So these are my 2 protons. It is feeling the effect of this. So this could be either spinning and it could be either reinforcing the external field or it could be opposing the external field. The protons which feel this will be slightly de-shielded. The protons which feel this will slightly shielded, and that is why you are getting 2 peaks for this, which is a doublet. Now, whatever is the effect felt by this due to this, obviously the same effect is going to be felt by this because of the presence of these 2 neighbors. So let us see how that works out. For this proton, I am having these 2 protons on the neighboring carbons. So at any given time, I can have both these protons are parallel to the external field. One is parallel, the other is anti-parallel. So you have 2 possibilities, and the third is both are anti-parallel. Now, this proton, which is feeling this effect, will be slightly de-shielded. If it feels this, there is no change because they are going to be cancelled. You will get a peak at the center. And if it is feeling this effect, it is going to be slightly shielded. So that is why you're getting 3 peaks for this particular proton. And the intensity is 1:2:1. Why is it 1:2:1? The total probability is 1, 2, 3, and 4. The probability of this is 1/4. This is 2/4, and this is 1/4. So that is why the intensities are in the ratio of 1:2:1. If I have a CH3 group, adjacent CH3, there are 3 protons. Again, the possibility is all 3 are parallel, all 3 are anti-parallel. These are the extremes. In between, you will have 2 parallel, 1 anti-parallel. Now, there are 3 protons, so there are 3 possibilities. 2 parallel, 1 parallel and 2 anti-parallel. Again, you have 3 possibilities. So the proton which feels this, so this is CH3 or ethyl bromide. The proton which feels this is going to be de-shielded, feels this slightly de-shielded, this is shielded, and this will be slightly more shielded. So I will get 4 signals, 1 for this, 1 for this, 1 for this, and 1 for this. And what will be their intensity? 1:3:3:1. Similarly, adjacent CH2 will give me a triplet, which we have already seen. So the n+1 rule is, if I have n non-equivalent protons on the adjacent carbon, then it is going to be split into n+1 peak. No protons, it will be a singlet, 1 proton, it will be a doublet, 2 protons will be a triplet, and the intensity of the split peaks will be given by the Pascal's triangle, which you are all familiar with. You can also calculate the intensity of the split peak by taking the coefficients of the expansion of a plus b to the power of n. So for example, n is equal to 2. So it is going to be split into 2 plus 1 triplet, and a plus b squared is a squared plus 2ab plus b squared. The coefficients are 1 and 2 and 1. If you take a plus b cube, then a cube plus 3ab squared plus 3a squared b plus b cube. So it is 1 is to 3 is to 3 is to 1. So you can do that also, and you can also find out from the Pascal's triangle. So a first order spectrum is, now look at this molecule, 2-bromopropane. This has these two methyls are equivalent, and which is different from this methyne. So if I were to calculate the multiplicity for methyl, it has got only 1 adjacent proton, so this is going to be a doublet. But if I have to consider the multiplicity for this, it has got 3 plus 3, 6 protons. So 6, n is 6. So this is going to be a 7-line multiplet. This is a first order spectrum. But suppose n is not the same on either side. Let us consider 1-bromopropane. Now this CH2 has got 2 on the adjacent. So this will be a triplet. This is going to be a triplet. But what about this CH2? I cannot consider this as 3 plus 2, 5, n equal to 5, and say that this is going to be a 6-line multiplet. Why? Because these 3 protons are different from these 2 protons, unlike the earlier case where both of them were equivalent. So here I should use the formula n plus 1 into m plus 1. If this was not there, this would have been split into a quartet. If this was not there, this should have been split into a triplet. Now both of them are there. So what happens is the quartet is further split into a triplet, and you get 12 lines, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you can draw the tree and measure the coupling constant. One of these coupling constants, JBC, will give me this coupling, and the other one will be JAB. So you will get both the coupling constants by drawing this tree diagram. So the spin-spin coupling, protons on carbon-carbon double bonds give characteristic splitting patterns. So if you have a di-substituted double bond, you can have geminal protons, you can have cis protons, vicinal, or you can have the trans protons. And by measuring the coupling constant, you can figure out whether it is with this isomer, or whether it is a cis isomer, or whether it is a trans isomer, because characteristic coupling constants for the three different types of di-substituted alkenes. So you see that a trans coupling is always higher than a cis coupling. So the separation of lines is going to be more here. The coupling constants we have already seen. Okay. Now, if 2 protons are coupled, you have what is known as a roofing effect. That means there is the leaning of a multiplet. A multiplet often leans upwards towards the protons that are causing the splitting. So this is characteristic ethyl group, 3 triplet and a quartet. If you see the roofing is, this is going to be upwards in this direction. This is pointing this, indicating that these two are coupled. Similarly, you have this isopropyl group. So you see that there is the roofing pattern. So this also gives you one hint about what is the nature of the protons which are coupled. I mentioned about long range coupling, W coupling. So this, if you see, resembles a W. So this is known as a W coupling, and it can have, in some cases, give you a good, for example, if you see here, this is a W. Okay, so 2.5 hertz. This is a W, HAV is a W. This is a W. So sometimes you get long range couplings also because of the molecule being in such a way that it resembles a W coupling. Madam, should I stop now? Dr.
Yes,
Kalpana?
yeah.
It's 4:30. You want to take a break now?
Yeah, ma'am, you have completed this PMR.
I have not. I've got little bit in PMR, and then I will start CMR.
CMR, okay. So can we take 10 minutes break?
Yeah, that's what I said. So you had suggested. So that's why I'm asking, shall I take a break now?
Yeah, 10 minutes break we can take.
Yeah, yeah.
Okay. So, participants, madam is, we are just breaking for 10 minutes. But we are not switching off the meeting. Meeting is as such, session is going on. So be here, don't log out, and we'll just resume after 10 minutes. This is 4:34. So we'll just resume at 4:45. Okay. We'll resume at 4:45 exactly. Thank you, ma'am. For 10 minutes, it's a break. Excuse me, madam.
Yeah, can we start?
Yeah, ma'am. Should we start? I think. Okay, participants, are you there? So, madam is just resuming her session. Please, ma'am, go ahead.
Okay, so we had discussed about the long W coupling. So,
okay, please mute your audios. Participants, mute your audio.
okay, we were discussing about the long range coupling.
Yeah, ma'am.
And so this is the W coupling. If you see here, this is resembling the W. And depending on what is the molecule, you can have different values for the W coupling. Now the coupling constant, the magnitude of the splitting is dependent on the number of bonds. For example, if you see JAB, of course, there has to be a substituent. Then you have JAB, it is ortho coupling is 9.4, the meta coupling is 1.1, and the para coupling would be around 0.9. So the closer the distance bonds, if you see this is 1, 2, 3 bond coupling, this would be a 4 bond coupling, which is a W coupling, this would be a 5 bond coupling. It is also a function of the bond order. So if you see here, this is an sp3. So here the coupling is 8 Hertz. It is a 3 bond coupling. Here, if you see, this is an sp2, it increases, and here it is 9.1. And it is also dependent on the angles between the bonds. Like I said, the trans coupling is always of a higher magnitude than the cis coupling, and the geminal coupling is a 2 bond coupling, which is very, very less. It is also got to do with the dihedral angle. And if you talk of conformations, if you see, in fact, Karplus equation gives you the relationship between the dihedral angle and the coupling constant. We are not going into the details of that. So the dihedral angle, if it is 0, then you see that the coupling is around 7 to 11 Hertz. When it is 60 degrees, it is 2 to 5. When it is 90, it is almost 0. And when it is trans anti-coupling 180 degrees, it again is 8 to 15. So that is given by the Karplus equation. So the coupling constant, the magnitude, is a function of all these factors. Now, I mentioned that we will be seeing what is meant by a first order spectrum. So a first order spectrum is one where the ratio of the difference in the chemical shift to the coupling constant, this should be much larger than about 8, where delta nu is the distance in Hertz between the midpoints of the coupled multiplets, and J is the coupling constant. And if this is satisfied, you can use the formula of n plus 1 for the multiplets, where n is the number of neighboring protons with the same coupling constant. Remember, the simple first order multiplex is centrosymmetric. If you see the triplet which we drew, it is symmetric about the center. If you see the quartet which we drew, that also is centrosymmetric. So there, if it is a centrosymmetric, then it is a first order spectrum with the most intense peak central, which we have seen in the Pascal triangle. Now the coupling constant, in order for that, you should see whether the protons are chemical shift equivalent as well as magnetic equivalent. The coupling will occur only between non-equivalent nuclei. So if they are chemical shift equivalent, they may or may not be magnetic equivalent. We will see that shortly. For no coupling to occur, nuclei has to be both chemical shift and magnetic equivalent. So if you consider the methyl protons here, CH3, CH2, CH3, the H1, H2, H3 are in identical environments. They are equivalent and they do not mutually couple. These are not coupling each other. Now look at this molecule, chlorobenzene. This HA is closer to this ortho, whereas this is meta. So obviously they are not chemically in the same environment. So HA and HB protons are in different environments. They are not equivalent and they are coupled. For chemical shift equivalence, if you are able to interchange the nuclei by any symmetry operation, for example, here in benzene, all the protons are chemically equivalent. If you consider trans 1,2-dichlorocyclopropane, these CH2 protons, they are chemically equivalent. Similarly, your axial equatorial, if you are in cyclohexane, because of the rapid exchange, the flipping that takes place, you are not able to see the difference and you find that they are chemically equivalent. Similarly, if you have free rotation about a sigma bond as a result, which is very rapid, as a result of which these protons cannot be distinguished and they turn out to be chemically equivalent, chemical shift equivalent. Now, what is meant by magnetic equivalence? In order to see whether a set of protons is magnetically equivalent or not, you have to first ensure that they are chemical shift equivalent. So they must couple equally to each nucleus in every other set of chemically equivalent nuclei. For example, if you take 1,2-dichlorobenzene. Now this HA and HA prime, they are having the same environment, they are chemically equivalent. Similarly, HB and HB prime, they are having the same chemical environment, they are also chemical shift equivalent. But look at the coupling of HA with HB and HA with B prime. This is an ortho coupling. This is a meta coupling. And you know that ortho and meta are not of the same magnitude. So although they are chemically equivalent, they are not magnetically equivalent, because if they were magnetically equivalent, then this should have been, the coupling constants should have been same for coupling of this with this and this with this. Similarly, AB prime coupling constant is not same as A prime, B prime. So these are chemical shift equivalent, but they are not magnetically equivalent. Similarly, if you see this, HA and HB, they are chemically, they are having the same chemical shift, but they are not magnetically equivalent, because this HAHC, the coupling constant, is different from HAHC prime. So non-magnetically equivalent nuclei can lead to complexity, and that would lead to a second order effect and very complex splitting patterns. So chemically, they may be shifts, they may be having the same chemical equivalence, shift equivalence, but magnetically, they are not having the same magnetic equivalence, as a result of which splitting is going to be different. It is going to lead to second order or complex spectra. Now, description of the spin system. How to label the spin systems, I'm not going into the details, but just explaining with some set of examples. So each unique set of spins is assigned a letter from the alphabet. So the total number of nuclei in the set are indicated as a subscript. And the relative chemical shift difference is represented by separation in the alphabet. So if you see CH2Cl, CH, if there is a large chemical shift difference, then you use the alphabets A and X or AMX. If the chemical shift difference is small, then one after the other, you represent them as AB. You can also have mixed systems where you have ABX, and magnetically non-equivalent nuclei which have the same chemical shift, but they are differentiated by using AA prime, XX prime, or you can write them as AX2. For example, these are chemically, they are equivalent, but magnetically, they are not equivalent. So you can write them as AX2 outside the bracket 2 or AA prime, XX prime system. This is an example of A2, and this is X system. This is an A3, this is an X2. Now here you see these two have got very close chemical shifts, and that is why this is labeled as an AB system. So this labeling helps us to figure out, especially in the case of complex spectra and all, very often you label what is the splitting that is happening. Is it an AX type of splitting? Is it an ABX? Is it an AB type? You have different patterns for them. Now, how does one simplify a complex spectrum? One method is by spin decoupling, which is a powerful tool for determining the connectivity of the protons and also assigning the proton peaks. I'm trying to explain this with very simple example. So if you take propanol, you see that there are going to be 4 signals, one for the OH. This is going to be a triplet. This will be not exactly a sextet. It is, though, if you go for a 60 megahertz, you may see it as a 6-line pattern. But ideally, this should be 3 plus 1 into 2 plus 1. So it would be a 12-line multiplet. Okay. But if I want to measure the coupling constant, I can do that by simplifying. And what do you do in that? You irradiate one proton in a spin coupled system, which removes the coupling. For example, if you irradiate this proton, there are techniques by which you can do that. What happens is this CH2 will not feel the effect of this. It will feel only this methyl. So what was a 12-line pattern will now become a 4-line quartet. If I irradiate this, this is going to see only the CH2. So this this multiplet would be reduced to a triplet. So by doing this irradiation spin decoupling studies, it is possible to simplify the complex spectra. Another way is the nuclear over-Hauser enhancement. This is basically if you want to find out which groups are coming adjacent to each other, or this is a through space more in for if you want to see what is conformational studies or what would be the stereochemistry. I'm trying to explain it with a very simple example. Uses much weaker irradiation. A proton which is closer in space to the irradiated one is affected irrespective of whether it is coupled to it or not. If it is coupled, then it retains some coupling. But if it is not coupled, there is going to be a change in the intensity of that signal, and the distance up to which this interaction can take place is up to 4 angstroms. The NOE is actually very less. So what you normally take is the NOE difference spectrum. So for example, I want to distinguish between these two isomers. Now what I do is I irradiate this methyl proton, and I have 2 protons. And if I see that only one of them is affected, the other one is not affected, that means this is going to be the structure. If it was this structure, by irradiating this, what is going to happen? Both of them are going to be affected because it is close to this, and hence I can use the NOE difference spectra to figure out which of them is going to be the structure. I have shown the example of this. So this is the molecule. This is the methyl at the 3 position. This is the methyl at the 5 position. This is the normal proton NMR spectrum. Then you're irradiating this methyl. So what happens when you irradiate it? This is going to be affected because of its proximity. This is not going to be affected. So when you take the difference of the spectrum, you find that this peak has disappeared, but there is an enhancement of this particular signal. If I irradiate this, then I find that both of them are going to be affected. I'm seeing that there is an enhancement of both these signals. So I can figure out which signal corresponded to this methyl and which signal corresponded to this methyl. Okay, now just a quick, if you can just do this problem, 1 minute. Compound is given. It has a strong absorption at 1150, but no absorption in this. So what the PMR shows a singlet at 3.5 ppm suggests a structure for this compound. So basically, when you're given the molecular formula, you can find out what is the index of unsaturation. Now there is an oxygen, but there is no peak at 50. There's no peak in this region. So obviously there is no hydroxy, there is no carboxylic group. So there's only a single peak. That means all the protons are equivalent and highly de-shielded. So they are attached to oxygen. So what is the structure for the compound? This is the structure. It is 1,4-dioxane is the structure for this molecule. A compound with the molecular formula is given. It gives me a singlet at 1.6 ppm, a singlet at 3.1, and a multiplet at 7.2 corresponding to 5 protons. So the most likely structure for the compound would be. Dr. Kalpana, I'm not able to see the answer. So if anybody writes the answer in the chat box, can you please tell me?
Okay, ma'am, let me tell. Actually, madam, we have disabled that chat.
Okay,
so
okay, fine. Okay.
Let them raise their hands. Participants, you can raise their hands. If somebody wants to answer, please raise their hands. I will just unmute them. Participants. Administrator, can you see some hands?
It's okay. I think we'll not, this time is going. So the answer is actually 2 because you are getting 3 signals. So this is the only one which will give me 3 signals. 1.6 would correspond to this. And you have The 3.1 is these two methyls, and 7.2 is your aromatic. If it was this should have given me 1, 2, 3, and the aromatic protons. This should have given me again 1, 2, 3, and the aromatic protons. This would have given me a quartet. I mean 1, 2, 3, and the aromatic protons. So this was the only one which would fit into this, and this would be the structure for the compound. Okay, now we move on to carbon-13 spectroscopy. So there is a basic difference between the proton and the carbon-13. Unlike the proton, the carbon-13 peaks are all singlets, normally singlets, and there's a large chemical shift range compared to the proton. The carbon-13 peak intensities do not correlate with the number of carbon atoms. If you recollect, in the case of proton NMR spectrum, we said that the integral ratio gives me the number of protons, but in case of carbon, that is not the case. And you need larger samples and longer times if you want to record the carbon-13 spectrum. The scale is much smaller in the proton NMR, which is only from 0 to 10. But in case of carbon-13, it goes 0 to 200 ppm. And why is this so? This is because the variation in the chemical shift is a measure of the shielding of the nucleus, and around the carbon you have got 8 electrons. So the electron density, less charge change possible in the distribution of 2 electrons around a hydrogen nucleus than in the case of the 8 valence electrons around the carbon nucleus. So that is why you find that the variation in the chemical shift is so high for the carbon. And this is the region for the carbon. You have the alkanes, the halogens attached to the carbon, the acetylenic carbons, you have the olefinic and the aromatic and the carbonyl carbon. So the approximate chemical shift, and most of these values are about 15 to 20 times the chemical shift of the corresponding proton in that region. Again, this is a standard textbook. You would get these data in any reference book. Now, spin-spin splitting, unlike the proton, you cannot get a spin-spin splitting in the case of carbon-carbon splitting. And why is it so? Because the 13 carbon, the abundance is only 1.1%. So the probability of having two carbon-13s coming adjacent to each other is very, very negligible. So that is why you do not observe splitting between carbon and another carbon. However, you can observe a splitting between carbon and an attached proton. So carbon will magnetically couple with attached protons and adjacent protons. And if you see the coupling constant for a one bond carbon hydrogen coupling, it is very high, 110 to 320 Hertz, whereas the 2 bond and the 3 bond, the values goes on decreasing. And these complex splitting patterns with great overlaps are difficult to actually interpret in the carbon spectrum. So if you see, this is the spectrum for cholesterol. You can just see the mess that is there here. So many peaks are there in this particular spectrum. So it is difficult. This is the proton coupled, because the carbon can couple with the proton. So this is the proton coupled spectrum, and this is the proton decoupled spectrum of cholesterol. So in the proton spin decoupling, to simplify the spectrum, a technique called as proton broadband decoupling is used, where the protons are continuously irradiated over a broad frequency range so that they are rapidly flipping and are not able to couple. And what the carbon nuclei sees is an average of all the possible proton states, and each different kind of carbon gives a single unsplit peak because the carbon hydrogen splitting has been eliminated. So the cholesterol, which gave so many signals, when you do the proton decoupled, the number of signals has come to 27. So this is a spectrum which combines both the PMR as well as the carbon-13. So you have the PMR for this, you have an aldehyde, so that comes at 9.4 ppm, and you have these which are all the aromatic in the aromatic region, and you find that they are coming here. And if you see the number of hydrocarbons, you have 1, 2, 3, 4, and this carbon. So you have 1, 2, 3, 4, and you have this 5th carbon. So you see that they are all singlets because these are all decoupled spectrum. Similarly, you have 1,2,2 trichloropropane. So you see here 1,2,2 trichloropropane. This is the methyl proton. This is the methylene proton. This is attached to Cl, so it is de-shielded. And you see that this is, both of them are singlets because they are not coupled to any other proton. And if you see the proton carbon 13, this is the methyl, and this is this carbon, and this is this carbon. Now this carbon, which is not attached to any hydrogen, is referred to as a quaternary carbon. You can have methyl carbon, you can have methylene carbon, you can have methine carbon, and you can also have a quaternary carbon. We move on now to how does one further simplify or get some more information about carbon framework from the carbon 13 spectrum. And we make use of what is known as the distortionless enhancement by polarization transfer, or known as the depth. Now here what happens is you give variable pulse. We are not again going into this because I am not familiar with all these pulses, etc. How they are done exactly. But what information do you get? So in the depth is a modern technique which provides the same information as an off-resonance technique. All the peaks remain decoupled singlets, and there is a transfer of polarization from the attached protons to carbon. The number of protons determines how this transfer occurs. So what happens in the depth? You first take a normal decoupled scan or a normal decoupled spectrum, in which each type of carbon 13 nucleus appears as a singlet. Then you give a pulse of 90. So the depth 90 scan, what output you get is only the CH carbons are seen in the depth output 90 scan. Okay? So exactly one proton will appear. Then you have the depth 135 scan. So first you take a normal spectrum, then you do a depth 90 scan, get the output. Then you do a depth 135 scan, in which the methyl groups and CH groups appear normally, but the CH2 groups give negative peaks. Quaternary carbons, which are not bonded to any protons, do not appear in any of the depth spectrum. Please remember that. So let us see the summary. If this is a quaternary carbon, no protons, normal 13 carbon, it will give me a peak. When I do a depth 90, I will not get any peak for the quaternary, neither will I get a peak for this. When I take a methine proton, I'll get a normal peak. When I do a depth 90, I will get a positive peak. When I do a depth 135, I will again get a positive peak. If it was a methylene protons, 2 protons are there. Normally it will give me a peak. Depth 90, it will not reflect. Depth 135, it will give me a peak, but it will be a negative peak. And methyl protons, 3 protons, normally it will give me a peak. Depth 90, it will not give me a peak. Depth 135, it will give me a normal peak. So I can distinguish between the carbons, the peaks, whether it is corresponding to a methyl carbon, it is corresponding to a methylene carbon, or is it corresponding to a methine carbon, by doing the depth studies, running it at depth 90 and running it at depth 135, and you can see this. So let us see, this is my molecule CH3CO, CH, that is methyl vinyl ketone. Okay, so it has got 1, 2, 3, 4 carbons. So I should get 4 peaks. So I'm getting 1, 2, 3, 4 peaks. Now, this is the normal spectrum. This is a quaternary carbon. So the quaternary carbon comes here. Okay, this is B. You have, this is A at 26 for the methyl. This is 129 for the D. And this is again 137 because of the influence of the carbonyl slightly downfield. Now, when I do a depth 90 for this, what you observe is only this proton signal will be seen, the other signals will not be seen. When I do a depth 135, this signal will be seen, this signal will be seen, this will also be seen, but because it is a CH2, it is going to have a negative peak, or it will reflect as a negative peak. So when you do the depth studies, and if you see that in depth 135, I'm getting 3 negative peaks, that means my molecule contains 3. If there are 3 peaks, negative peaks, that means my molecule contains 3 CH2 groups. If I do not see any negative peak in the depth 135, then I can be sure that my molecule does not contain a CH2 group. Depth 90, it gives me a peak, positive peak. That means I know that my molecule contains a CH carbon in its framework. So by making use of this depth technique, one can figure out how many CH2s are present, how many CH peaks could be present, how many methyl groups could be present. So especially when you have complex spectra, this can simplify the spectra. So I would like you to do this quickly. Suggest a structure that is consistent with the following carbon-13 NMR data collected using off-resonance proton decoupling experiment. So you're given the molecular formula and you're given the carbon spectrum. So based on this, are you able to assign what is the structure for this molecule? So molecule, you can calculate what is the index of unsaturation. So it will come out to be 6. Now you see that you have a quartet at 30. So that means when will carbon be a quartet? When it is a methyl group attached to 3 protons. So that means this corresponds to a methyl group. This is a triplet. So that means it is a methylene group CH2. This is a doublet. So that means this is CH, this is CH, this is CH, this is C without any protons attached to it. This is also a carbon, which is a quaternary carbon. So these 2 are quaternary carbons. These 3 which are appearing as doublet is due to CH, and this is CH2 and this is CH3. So this region, if you see, is of the aromatic region. So the structure of my compound is, this is the structure. So this is my methyl, which is a quartet. This is the quaternary carbon, which is 205, which is a singlet. This is CH2, which is a triplet at 50. These are the aromatic protons, and this 137 is this quaternary carbon of the aromatic ring, which is substituted. So using the data, it is possible for us to solve the structure of the compound. So we now just more quickly, I would like to go through what is meant by 2-dimensional NMR spectroscopy. Now, what we have seen till now, the proton and the carbon-13 NMR spectrum is actually a plot of frequency versus intensity. That means it is actually a 2-dimensional spectrum, but we call it as 1-dimensional because the 1-dimensional we are referring to frequency. And what we call as 2-dimensional spectrum is actually a 3-dimensional plot. The 2-dimensional in this case, both of them are frequency axis and the intensity is omitted. We are not going to discuss the pulse sequences as to how one generates the 2-dimensional NMR spectrum. So here you have different techniques. You have correlation spectroscopy, you have head core, a lot of modified techniques are there, but I'm just going to give you a feel of what is the 2-dimensional NMR and how does it simplify spectra and how it can be used for structure elucidation. So this is the 2-dimensional NMR spectrum for this molecule. If you see, this is 3-methyl-1-butanol. Now you have both these axes. This is a correlation spectroscopy, 1H, 1H, COSY. COSY stands for correlation spectroscopy. Now, on the x-axis, this axis, as well as this axis, you have the proton spectrum. The normal 1-dimensional spectrum is seen on both these axes. If you see here, this is the 1-dimensional spectrum. This is also the same 1-dimensional spectrum. Now, in the 1-dimensional spectrum, if you see, I should get 1, 2, 3, 4 signals because there are 4 different types of protons. This proton should be the most de-shielded because it is attached to the oxygen. Neighboring carbon has got 2 protons, so this should be a triplet. This has got 2 protons on this side, 1 proton on this side, so m plus 1 into n plus 1. So 2 plus 1 into 1 plus 1, so 3 into 2. So you will get this as a multiplet, a 6-line multiplet. This is going to be a doublet because of this presence of 1 proton on the adjacent carbon non-equivalent. And if you look at the CH proton, it has got 2 protons here and 6 protons here. So it is going to be a multiplet of 6 plus 1, 7 into 2 plus 1. So 7 into 3, a 21-line multiplet is what one would expect for this. Now, this is the 2-dimensional. So what you have is, you have this diagonal peaks. Okay. So your main spectrum is there. You have the diagonal peaks. You normally take them in sections, and you have cross peaks. Now, these cross peaks are very, very important because these cross peaks tells you which proton is coupled to this. For example, let us take this. This corresponds to my H4. Now, if H4 is coupling to H3, then I should be able to see a cross peak between H4 and H3. So where does my H3 come? This is my H3, and you see that there is a nice cross peak. By what do you mean by cross peak? I should be able to, sorry, you should be able to complete this. It should form a square. So this is my signal at H3. This is correlated with the proton on H4, and that correlation is shown by means of this square. Similarly, H2 is also coupled with H3. So this is my H2. You see that there is a cross peak for it with respect to H3. So if I draw a line from H3 to this and draw this, it will couple with this. So this is forming a square. So that means this proton is coupled with this proton. This is forming a square. So that means this proton is coupled with this proton. Now you're also able to see another square being formed by this proton with this. So what is this proton? This is my H1 proton, and it is coupled with H2. So you see that I'm able to have a correlation by way of this cross peak, and you see that this is the correlation. So using the COSY, it is possible for us to figure out which are the protons which are coupled. Now this is relatively a simple molecule, but imagine you have a very complex molecule. You will see that there will be several cross peaks, and even with a COSY, you may really not able to interpret and arrive at the structure of the compound. You may have to do further investigation and do other more advanced techniques. But I have just shown this to give you a feel of what could be, how a COSY spectrum will look like, and what information you can draw from the COSY spectrum. So this was a proton-proton coupling COSY spectrum. You can also have, look at this molecule. This is butyl ethyl ether. Now here you have A, B, C, D, E, F. You are having 4 plus 2, 6 protons, which is going to be the most de-shielded. Obviously, you have CH2, CH2, both are attached to oxygen. So you see, they're going to come very close together. This is going to be a quartet. This is going to be a triplet. Now, you really cannot make a quartet and a triplet here because they are merging together. This is going to be a multiplet. What will be the lines? 2 plus 1 into 2 plus 1. So it's going to be a 9-line multiplet. This is also going to be a multiplet, which would be a 12-line multiplet, 3 plus 1 into 2 plus 1. This is going to be a triplet. So the methyl triplets at the end of the chain, they are normally very clear because they are adjacent to a CH2. So you are able to see that clearly. This is my proton A. This is the other methyl, which is also the triplet. The mess comes when you have this, and these two are coming close together. So this is the structure, and they are downfield because of the effect of the oxygen. Now, if you run the two-dimensional 1H, 1H cozy for this, this is what you would get. You see that this is coupled with E. So where is my E? My E is here. And you see I'm having a cross peak. And with this cross peak, I can say that this corresponds to the CH2 proton of next to this methyl. Now you see that E is coupled to D. There is only this coupling. There is no other coupling for this E. One is already accounted for. The other is this square, indicating that this is the signal which corresponds to protons on carbon number D. Now D is attached to C. Now you should have a cross peak from D to C. So you see here now, here they were merged. You can see that actually there is a slight difference because this cross peak is slightly different from this cross peak. So I'm able to draw a line from this to this to this, and you see that this is corresponding to my HC, and A is correlated to B. So you see that there is a cross peak from A to B, and this is what you get. So what was complex here? In the two-dimensional, they are still close, but you can still see there is some difference in their cross peaks, and that is enough for you to predict what will be the coupling constant and what is going to be the chemical shift, exact chemical shift for these protons. You also have what is known as head core. Head core is heteronuclear correlation spectroscopy, where you have, in the earlier case, you had both X and Y axis were corresponding to the proton one-dimensional spectrum. In the head core, on one axis, you will have the proton. On the other axis, you are going to have the carbon-13 spectrum. So here you are going to correlate the carbons with the corresponding hydrogens. So again, the same molecule. So you see that this is CH3. So here you do not have the diagonal thing. The diagonal was for the cross peaks when you had the proton-proton. Here you do not have the diagonal. Instead, this proton is, if you see, draw a line, it gives me, directs me to this carbon. So that means this is the carbon which is attached to this F. If I draw a line from this, extend it here, I find that this is correlating with A. So that means this is the carbon which is this methyl. If I draw a line from here, this is correlating with this, indicating that this is carbon, this is the carbon. If I draw a line from this, it is coming here. That means this is corresponding to D. Similarly, now you see here, if I draw a line from this, I find that it is correlating here, and this is correlating here. So based on this now, otherwise it would have been difficult for you to identify which CH2 is which, but from the proton cozy, you figured out which was B and C, and now from the head core, you can figure out which carbon corresponds to B and which carbon corresponds to C. So by using the head core, by using the cozy, it is possible for us to simplify complex spectra. I have still taken a fairly simple molecule, but you can still have very, very highly complex molecules. Requires a lot of time, requires a lot of patience to interpret these spectra because they do not come. You can really have spectra, two-dimensional spectra, where you can have a lot of contours here, a lot of mess, and to really figure out which is the peak, which is the cross peak, is going to be a tedious task. So with this, I have actually come to the end of my presentation. So what we have discussed is the basics of NMR. We saw that there are 4 features in the PMR: the number of signals, the intensity, the position, and the splitting of the signals. We also saw the chemical shift equivalence and magnetic equivalence. What are the difference between the two? Spin labeling studies, techniques to simplify complex spectra. I'm sorry, there's a spelling mistake here. Basics of CMR and how it differs from the PMR. And I also gave you a glimpse of what is a cozy and a head core. I think I finished well before time. So if there are any questions, I would be glad to take them. Hopefully, I should be able to answer them. Thank you very much. Dr. Kalpana?
Yeah, thank you, ma'am. Participants, you can raise your hands. When you will raise your hands, I will just unmute you. Okay, I have Sandeep Jha. Okay, Administrator, are you in? Please unmute Mr. Sandeep Jha.
So yes, ma'am.
Okay,
Yes,
please
ma'am.
please ask your question. Go ahead, Sandeep. Go ahead.
Ma'am, TMS has 12 active hydrogen, but its peak will be shorter.
Pardon?
What is the cause for it?
PMS has 12 hydrogens, yes.
It's मतलब in NMR spectroscopy,
Hmm?
its peak is smaller.
No, you normally get a very intense peak for TMS. You normally get a very intense peak for TMS because it is corresponding to 12 protons.
Okay, ma'am.
Satisfied,
you, ma'am.
Sandeep? Or you want to ask some other thing? Okay. Divya N. Administrator, please unmute Divya.
Good evening, ma'am.
Yeah, please go ahead, Divya.
Ma'am, how to decouple protons from a molecule?
See, there is actually, I mean, that instrumental techniques, I really don't know. They do vary the pulses and they find out at what frequency those particular protons are absorbing. And then they try to, I think, remove those frequencies and do the decoupling. I don't know exactly how the instrumentation is done, but it is a very useful technique for doing it. But I'm sure you will be able to get this in any standard textbook which discusses also the techniques for doing all these experimental, because this is more of an experimental part rather than actually the interpretation part. The application is more of the interpretation, but it is possible. You must be irradiating, so that particular frequency you are putting that particular frequency, so those protons, they are not shown in the spectrum.
Okay, thanks a lot, ma'am.
Administrator, please, there are some other participants. Atmadeepa Chakrabarti, please unmute Atmadeepa.
Good
Okay,
evening, ma'am.
yeah,
Am I audible?
Yeah, you are audible.
Yes, I'm asking you, ma'am, you have told about the delta chemical shift. Chemical shift is equals to shift in hertz by spectrometer frequency in megahertz. Delta may be positive. Delta is positive. May delta be negative?
You could have delta. There are certain extreme cases, I think some cyclopropyl derivatives and all, where you have the chemical shift going below 0 ppm also. There are exceptions, that's why I said there are some cases. I think some cyclopropyl derivatives, I don't know the exact ones, but yes, there are some compounds where you have chemical shift which can go below 0 also.
Okay, thank you, ma'am.
Richik Sarkar is there. I think Richik, I think, yeah. Richik
Yes, ma'am. Hello.
Yeah.
Please go ahead.
Hello, ma'am. Can you hear me, ma'am?
Yeah, you are audible.
Ma'am, I want to ask you, ma'am, one thing, ma'am. Ma'am, can you please tell me about the magnetically dilute and magnetically concentrated, that part?
Magnetically?
Dilute and magnetically concentrated systems, because you told the systems like that is A.
Hello?
I think we have
XM and AXM systems. Hello.
You're talking about the labeling?
Hello, ma'am.
You're
Yes, ma'am.
talking about the labeling?
Yes, ma'am. Yes, ma'am. Absolutely.
Okay. See, that labeling is actually, first you have to see how far that you have to take the ratio of the chemical shift difference to the coupling constant. If that ratio is greater than 8 or greater, then it is a first order coupling. Now, if it is less than 8, okay, now you have to see what is that ratio. If that ratio is somewhere around 1 or 2, I mean, if it is around 2 or 3, then that means they are very, very close in their chemical shift. So that means you will be using the labels of A and B. But if that difference is quite large, then you take it as A and X. That means the alphabets are not very close. If it is in between, then you use the terminology M, A, M, X. So that is basically, you have to use those labels by taking the difference of the chemical shift difference to the coupling constant. If there's a large difference, then you will use alphabets which are far away from each other. If the difference is very close, that means that ratio is very, very close, then you will use the alphabets which are close in the alphabet sequence. Does that answer your question?
Yes, ma'am. Thank you, ma'am.
Okay, thank you, ma'am. Minita Oja.
Yeah, good evening, ma'am. Hello.
Yeah, good evening.
Yeah, ma'am. I just want to ask about 2D NMR hat core, ma'am.
Yeah.
Okay, ma'am. As you explained in 2D NMR hat core, we found dots which can be correlated to 1H NMR on one side and 13C NMR on the other side.
Yes.
Okay, ma'am. But often in my 2D NMR, what I find that there is a straight line of dots which cannot be correlated with either 1H or 13C. And in every 2D NMR spectrum, I find a straight line of dots. So, ma'am, what may be the reason for that?
Is it with head core or is it also in COSY?
No, ma'am, only in head core. COSY, I didn't require to get
I
anything.
will say you should do a COSY.
Okay, ma'am.
You see in this, I showed you this BC, HB and HC, those protons were coming very close.
Okay, ma'am.
You really don't know which one is corresponding to the carbon of HB and HC. So ideally you do to COSY and then do your head core. I think that might be helping you to solve it better.
Okay. Thank you so much, ma'am. Thank you so much.
All the best.
Pradipta D. Pradipta D, please ask your question.
Ma'am, why isn't the coupling constant value that is measured in hertz not a function of the operating frequency of the NMR machine?
Because see, that is not affected by your induced magnetic field. Okay, it's spinning all right, but it is not going to be affected by any induced magnetic field. The number of, it has got basically to do with the order. I told you the bond distance and the hybridization and also the dihedral angle. And these factors are not going to be affected by the operating frequency of the instrument.
Okay, ma'am. Thank you.
Shubham Ojha.
Hello, ma'am. Good evening.
Good evening.
Am I audible?
Yes.
Ma'am, like in NMR, we can differentiate between the axial and equatorial protons of the cyclohexane ring if we carry it out at lower temperature.
Yes.
Now, if I take 1,1-dimethyl cyclohexane, can I use CMR to differentiate between those axial and the carbon at
1,1-dimethyl cyclohexane?
Yes, ma'am. Can I use
you
CMR to differentiate between those?
You're saying you're doing it at lower temperature?
Yes, preferably.
Because if you do it at room temperature, you will see only one signal for that.
Yeah, but at lower temperature, can I differentiate?
At lower temperature, it could be possible. And it is both are methyl groups. So it is possible, it should be possible, provided you may have to go to -70 or something. Because you have to arrest that flipping.
Okay.
But then both of them are going to be methyl. One is axial, one is equatorial. So ideally, axial equatorial, there is a slight difference. Even if you take cyclohexane, axial equatorial protons, there is a slight difference in their chemical shift.
Yes.
Okay. But that is observed only when you go to a very, very low temperature. So in that case, even the methyls should be able to give you that separate signals.
Okay. Thank you, ma'am.
Gaurav Dev.
Hello.
Yeah.
Good afternoon, ma'am.
Good afternoon.
Am I audible to all?
Yes.
My question is about that shielding and deshielding protons.
Yeah.
When the one parameter to determine the shielding and deshielding is the magnetic field, external magnetic field.
Could you please repeat it again?
One parameter to determine a proton, it is the shielding or deshielding. It can be use the external magnetic field.
Yes.
There is any
What is your question?
There is any parameter to determining this? Any other parameter?
I put it up. No, they are affected by the hybridization. They are affected by but basically again hybridization, the electronegativity percentage character is more, so more electronegative. So deshielding comes there also. So whichever way you look at it, there is going to be a deshielding and a shielding effect. It could be due to electronegative atoms. It could be due to the hybridization. It could be due to the induced magnetic field.
Ma'am, another question is, can I single proton? We can say about that is the shielding or deshielding, just only single proton.
On a single proton, it should be having some groups on the adjacent carbons, no?
Okay.
There has to be just a naked proton. You cannot have. It depends on what is the electron density around that proton. If there is a greater electron density, it is shielded. If there is no less electron density, it is de-shielded.
Okay, ma'am. Thank you, ma'am.
Ishita. Is Ishita there? She has also raised her hand. I can see that. Okay. Rachna. Can I see? Ishita, are you there? Please ask your question. Ishita.
Hello.
Yeah, ask your question, Ishita.
Ma'am, this is Rachna Sharma.
Okay, Rachna, ask your question.
Ma'am, actually I'm working over aloe vera gel. It is an organic compound. You already know. I have taken its NMR, but as its molecular structure is very complex, so it should have a complex spectra. But rather than that, I have got a singlet in the NMR spectra, and there are 3 or 4 peaks which are present, but they have not exactly shown the chemical shift value for those peaks. Initially, they have given certain ranges. For example, 4.327 to 4.701. Now, I am not being able to identify the signal because of which particular functional group it is coming.
See,
Because
from NMR,
there
you
is
do
no
not.
singlet or doublet or triplet is being shown in the spectrum.
What is your operating frequency of your instrument? And I mean, is it 250 megahertz, 300 megahertz? What is the operating frequency?
Ma'am, it was, I think, 250 megahertz.
I have increased the resolution of your, increase the operating frequency, you take it in a better, higher operating frequency, the resolution is going to be much, much better. And you might probably see the splitting much, much clearer.
Okay, ma'am. Actually, I have analyzed my sample in Soras University. Whatever instrument they were having, they just gave me the results. They were not even able to interpret the data whatever they are giving.
So because otherwise, if they are all, it's a complex spectrum, you may have to go for techniques to simplify the spectrum, like decoupling, or you should go. Did you do the carbon-13, etc.?
No, ma'am.
Yeah, so just with the PMR, if it is it may not be possible for you to interpret at one go. Try to see if you're able to do, and you need to actually see the structure of the molecule. Is it a reported compound?
No, ma'am. Actually, there are 250 different species of aloe vera gel, so it is very difficult to identify the actual chemical structure.
But then you will have to first, is it a mixture? Is it a mixture of compounds? All that you will have to see.
No, so it is a single extract that I have extracted from the plant, aloe vera gel.
That is a single extract, but does that extract contain a single compound? That's what I'm asking. Did you run it?
Yes, ma'am. It is itself as extract only. I have not added anything else.
No. I'm asking because very often when you do extraction also, if you take a GP, you may not find that it is a single peak. You may find that it is a mixture of compounds. So if you take a GP, probably you will know how many components are there in that extract. Extract may not give you only a single compound. That's what I'm trying to say. Okay. Especially the natural product extracts.
Yes,
okay, Mr. Ravindra Kumar will be able to take 2-3 questions more. Virendra Kumar. Mr. Virendra Kumar, are you there? Okay. Then Mr. Amar Srivastav. Administrator, please unmute them. Mr. Amar Srivastav.
I am audible.
Yeah. Mr. Virendra Kumar, please ask your question.
Ma'am, my question is that you said that the spin quantum number of proteum is half and nitrogen is 1. So we have to learn the quantum number.
Spin quantum number of?
Ma'am, you said that the quantum number of proteum is half. Spin quantum number of proteum
of hydrogen.
Yes, and nitrogen is 1. So we have to learn that quantum number, or there is a principle involved in it to find out that quantum number.
See, these quantum numbers are not difficult. I think you must have learned it even in your lower classes. What you should remember is, at least for carbon and proton, you should know that it is having half, because they have only 2 orientations when they align, either parallel or anti-parallel. Okay, these are the 2 nuclei which you are really going to be studying for your spectroscopy. The other thing is, if you know, you should realize that odd mass and odd atomic number, these are the nuclei which are actually NMR active. So if you remember that much is enough for you to know whether they are going to be NMR active or not. But yes, you should know that it has a spin quantum number of half. That is not difficult to remember if I I mean, if I can say so.
Ma'am, there's a principle I need, which we have to find that spin quantum number.
So that is more of a, I mean, that is more into theoretical realms, and that is quantum chemistry, which is not my forte.
So we can find it.
Yeah, that is possible. The spin quantum number and all those things, experimentally, it must have been proved, and all those things are there.
And the answer lie in the quantum chemistry.
Yes, that is more into that realm, which is, I am not familiar with that. But yes, it is possible to determine.
Thanks, ma'am.
Hello. Good evening, ma'am.
Good evening, sir.
I have a very small query. Nowadays, we measure the chemical shift by delta values in pp. In older books, it was measured in terms of tau.
Tau values, yes.
Right. Now, what was the problem with tau that it was replaced by delta?
I mean, that I'm really not, I don't think I'm in a position, but I would say that tau is actually TMS is 10.
Right.
TMS is taken as 10. So probably that confusion was there, and that is the reason, but you need to really go into the history of that to figure out. I'm really not aware of that, but this could be one reason. Very often that tau, when it is used, you have to remember that TMS, the standard is taken as 10, because very often when we talk of standards, we take it as 0. So probably that confusion could have been there, which is the reason why it must have changed. I'm not very sure.
Okay. Okay. Thank you, ma'am.
Yeah.
Ma'am, such is the impact of your lecture, ma'am, that still we have many hands which are being raised.
No, I don't mind answering.
Actually,
I don't mind answering if I can answer.
Ma'am, I think. Okay, ma'am. Let me see. Please, participants, if you have any question related to the lecture, we can take it. But please do not ask your research-based problems. We'll just mail them to madam.
My email ID has been, you can share my email ID, Dr. Kalpana. You can share my email ID, which was given in the slide.
Yeah, I'll do that, ma'am. I'll share the email ID of Madam Dr. Lakshmi Ravi Shankar with you. And in that condition, when the questions are there, you can definitely ask her directly, or you can mail these questions to Mother Science College @gmail.com. I'll just forward your questions to Madam. Madam, I would like to tell you here one thing, that this session is streaming live on YouTube also. So there is a one YouTube question. I would just want that you that you should take one question from there. Otherwise, they will think that we have not.
Sure.
There is a question that does the geometry of the molecule due to sp and sp2 hybridization responsible for its parallel and perpendicular orientation respectively in external magnetic field?
It could be possible, but nobody has really convinced me with that answer, because very often if you see what I was told was that it is more of an experimental observation, and when you place it parallel, the circulation of pi electrons is more effective, is what was told to me. But I still have not got a very convincing answer for that. So that is, I'm still looking out for a proper answer. But yes, if you keep it parallel, you get it as shielded. If you keep it as perpendicular, the acetylenic protons come out to be de-shielded. So yes, that is why it is known as an anisotropic effect, because the property depends on the direction. It is a property which is changing with the direction. And a lot of studies, they must have done detailed studies and found that in all the cases, the acetylenic protons are being shielded, and that can be explained only if you consider the acetylene being placed parallel to the externally applied field. It is possible that the geometry is there, but still I am not being convinced with that particular answer. So if anybody has got any material which explains this in a much better way, kindly share it with me. I'll be more than happy to go through it.
I think you took it in your lecture too. When you were just taking your lecture, then you just took this point too. So
yeah,
I think
I think that's the reason why that person is trying to justify that it could be because of the sp2 and the sp hybridization and the geometry, which could be the reason why. But still, I mean, this is really not I have not been very convinced with this, because even if you keep it perpendicular, I don't see the reason why it is going to be linear. It can still be placed perpendicular. So I'm really not convinced, but There must be some reason, or it is more of an experimental observation, like many people have told me.
Administrator, for once, just unmute Atma Deepa. She just again want to ask a question. For one question, unmute Atma Deepa. After that will wind up this session, question answer session.
I have two questions. You have told about spin coupling first order and complex second order.
Yes.
How can we understand at a glance?
See, I thought I mentioned, if it is first order, you will see that n+1 formula will be allowed. If it is first order, you will see that those peaks are centrosymmetric. If you recollect, in that slide, I had mentioned that all the peaks, the split peaks will be centrosymmetric. A quartet is centrosymmetric, a triplet is centrosymmetric. So it will follow the n+1 rule. But if it is an n+1 into m+1, it does not become a first order. If it is a low resolution spectrum, you may really, all these peaks may merge together and you may get a complex spectrum.
Okay, ma'am. And I have another question. In the slide of summary of DEPT, in DEPT 135, there is a downward peak for CH2.
CH2, yes.
Why is it? There is a downward peak.
Why exactly? Again, I'm saying, I don't know they apply some pulse and things like that. So it has to do with the electronic environment. I don't know the exact reason why it comes as a negative peak. My emphasis was more on the application part. But again, you would be able to get the answer to this if you go detailed into the theory behind the DEPT. How the pulses are applied, how the recording is done, all that would probably maybe give you an answer to your question. Can you suggest me, ma'am, a good book for this thing? You could see Silverstein spectroscopic analysis of organic compounds. You can also see Pavia, which has given a lot of spectra. I mean, combined spectra solving problems combined of IR, UV, mass, NMR, carbon-13. So Pavia is another book, and Kemp is there. Silverstein gives two-dimensional NMR also. It gives depth also. Pavia also gives depth, and their language in Pavia is very lucid, and it gives more of problems, and whatever concepts you need to know, that much is given very lucid manner. So I would suggest that book also.
Okay, thank you, ma'am. Thank you very much.
Welcome.
Participants, there are still many hands which are being raising. But participants, please, as looking at the time which we are having, which we are left by, I will be putting your questions in the mailbox of Madam Lakshmi Ravishankar, or I'll share the email ID with you.
Yeah, you can share the email ID, Dr. Kalpana. That would be better.
Yeah, ma'am. I'll just share the email ID and in the WhatsApp groups. So you can just ask directly your questions to ma'am. And now I will hand over this session to Dr. Dipendra Singh Raghuvanshi for further proceedings. Dr. Raghuvanshi.
Thank you, Dr. Kalpana Singh. What a session, wow. And I don't have words for that. I seen too many lectures, but this was absolutely brilliant. I mean, the theory and the explanation and the systematic presentation. We thank you very much, ma'am. Hats off to this presentation. I think everyone is benefited by this presentation. And even I had raised my hand, but then I put it down because not much time left. So maybe I will put my question into the mailbox too.
Sure, sir. Welcome.
All right, thank you. And I will now invite Dr. Arpan Bharadwaj, sir, Principal of Government Madhu Science PG College, that he may present his words on this presentation and on the future, what our college foresees with such brilliant presentations and the coming NMR scenario of this college. Dr. Arpan Bharadwaj.
Thank you, Dr. Dipendra. It's very difficult to say anything about this presentation, this session which we had today. Actually, what I was expecting, that is not only fulfilled, rather a more, more thirst of teaching methodologies increased. When we were listening about Madam's resume, her life and her achievements, I was it was better if you could telling about NMR, because what she has done in her career so far is tremendous. It's wonderful. It's not. It can't be reached by a normal a teacher like us. So I thank you, ma'am. It was really a wonderful experience. You are teaching. You are with us for last 2.5 hours, concentrating on NMR. Every aspect of the NMR, because I am also a man of chemistry, and especially of organic chemistry only. I can understand that you have not left anything untouched regarding NMR. Everything, all questions. Atmandeep Sarkar asked you one question that the values may be negative. You answered that very beautifully, that the cyclopropyl derivatives may be of that order. I would like to add that yes, metal hydrides, even 18 annulenes, bigger annulenes, they also show negative values of delta as well as positive values, because some protons are inside the ring and they show negative values. So it was wonderful. And बस यही कहूंगा मैम कि आपने आकर के you have enlightened us, you have teach us how to teach. That is what is important. So NMR, you have given the books by William Camp, books by Silverstein, books by Poaba, and so many more things you have shared with us. So it was really wonderful. The Vazde College itself, as I was a coordinator of pharmaceutical chemistry in our college. We are planning to visit your college because the distance to globally, in the field of perfumery and some that I have heard about that. So yes, as we teach in cosmeceuticals, we are teaching cosmeceuticals, we are teaching herbaceuticals, and I know that your college has association with some French companies even, and you are blending not only. And as your Wikipedia tells that you are there in agriculture also, and so that is this land of Madhya Pradesh, this Malwa region is a land of agriculture basically. We are not the people of industries. We are people of agriculture only. So when I was reading about your college, it was mentioned there that yes, your college is dealing a lot in the field of agriculture. So we'll be very happy to associate with you. We wish to visit your department of perfumes, and where you are doing all these things, wonderful things. And now I can understand that not only one segment of the college, rather the whole college is wonderful. Like you are doing your awards, your papers, your presentations, it was all wonderful. And we'll be very happy if we can invite you to Jan after the things become normal, and we'll have you for more time we want to spend with you. It is not for one day only. It cannot be. I cannot say that it was sufficient. So we will be very happy if you can be our guest for 2 or 3 days and can help us in teaching not only teaching subjects of the syllabus, rather teaching how to teach pedagogy. If we can develop through you, if you can learn how to teach, then basically we'll be supporting the education system. So I thank you once again, ma'am, and I request you to be with us, to remain with us when and whenever we need you. Thank you very much.
Could I just speak, Dr. Kalpana? Dr. Kalpana?
Yes, ma'am, I am listening.
Yeah. Thank you very much, Principal Sir, and it's really an honor for me also. And I always enjoy teaching, and I find when I interact with students, I learn a lot in the process. So I think as teachers, we are all learners, and we should continue to learn. And it has been a really wonderful experience making this presentation. And I thank you very much sincerely. The entire team, Dr. Kalpana has been very proactive and keeping in touch with me. Dr. Pare also has been in touch with me. Our association has gone. In fact, he has invited me to Ujjain. He had invited me earlier, but due to some reasons, I couldn't make it. I hope I should be able to, once things settle down, I hope that I get an opportunity. And you are also welcome to our college. Yes, we do have, our biotechnology department does a lot of work with the farmers and buyback policy. We have a postgraduate diploma in cosmetology management, which is one of its kind in the country, and they are doing extremely well. So you're all welcome to our college, to visit our college, and let's hope that this pandemic gets over and all of us are safe. And thank you very much for this. I feel very humbled actually. Thank you very much for this invite and giving me an opportunity to share my expertise. Thank you very much.
Thank you.
I would just like to call Dr. Jeevan Singh Solanki for official vote of thanks. Dr. Solanki, are you listening? Are you there? Are you there, Dr. Jeevan Singh Solanki?
Hello.
Yeah. Dr. Solanki is there or not?
Yes, ma'am. Hello. Yes.
Okay, so please unmute Dr. Solanki.
Hello.
Hello.
Dr. Solanki, you are invited for official vote of thanks. Please go ahead.
हेलो
जी सर.
मैडम एक मुझे और देंगे आप प्लीज.
हाँ जी सर.
एक्चुअली मैं आपसे कहना चाह रहा था कि अब जो हमारे इवेंट कल है 27th को 30th को वो भी पार्टिसिपेंट्स others we have a large number of participants with us and we have very important sessions tomorrow and on 30th and 31st. So if you please inform them about all those events, that
Yes,
will be really better before extending vote of thanks.
Yes, yes, sir.
Please.
I thought, okay, Dr. Solanki, be with us then. Let me give whatever sir is. Let me say. So then I will just post. I have just posted this in the chat box also that actually there is a session, extended session of this session. This is a joint training program for 2 days. That is on 26th and 31st. And this is a training program for junior faculty and students on this PMR, CMR, and there will be some fundamentals of organic chemistry which will be discussed on 31st by Dr. Amrit Krishnan Mitra. So that 31st lecture is a part of this lecture, this session, this training program. So you will be getting certificates only after you attend that session and give your feedback for that session too. So thank you very much. This is for 31st. Then now we are having a session, a very important session tomorrow also. That is 27th at 11 a.m. We have a session on health and happiness where we have two great personalities speaking on the issue. So we'll share the link with you. Please be with us on tomorrow also. That is on 27th also. It's a very good, there will be very good 2 lectures tomorrow. Then we have a session by Padma Vibhushan, Dr. Sonal Mansingh on 30th of July at 4 p.m. also. So please be with us. We'll be sharing with you the links and all the particulars of those sessions also. So thank you very much. I'll be posting you through WhatsApp groups. Now I invite Dr. Jeevan Singh Solanki for official vote of thanks. We will be posting feedback links after this Thanksgiving ceremony is over, and you will have to fill up this feedback by 7 p.m. which contains 4 to 5 questions by Dr. Lakshmi Ravishankar, which she have taught you. So you have to answer those questions and you have to fill up this form and submit back by 7 p.m. Dr. Solanki, please, floor is yours.
Thank you, ma'am.
Yeah.
It's my great privilege to propose vote of thanks and acknowledge the contribution to those who work really hard to make this event successful. I speak on behalf of Department of Chemistry, Pharmaceutical Chemistry, and entire fraternity of the college. First of all, my most sincere thanks to Madam Lakshmi Ravishankar, who spared time from his busiest schedule and deliver very fantastic, valuable, and informative lecture. Thank you very much, ma'am. We are also thankful to our principal, Dr. Bharadwaj, for being the catalyst that stimulate us to do best and extending the pillar of strength. Thank you very much, sir. I am also thankful to IQAC coordinator, Dr. Kalpana Singh, madam, head of the department, Dr. Brajesh Pare, and our technical team for their valuable suggestion and technical support. Last but not least, I would like to thank the people who work behind the scene to make this event successful. Once again, thanks to all. Thank you, ma'am.
Okay, thank you very much, Dr. Solanki. And thank you very much, madam, for being with us, for sharing your important time. Okay, participants, I
can forward the questions, whatever comes to
Yeah.
you, please forward them to me.
Okay.
Thank you very much. And all the best to all the participants.
Thank you, ma'am. I'll be, ma'am, forwarding your email ID to these participants.
Yeah, sure. You can give them my email ID. No problem. Thank you very much. Thank you, everybody. Good day.
Thank you, ma'am. We are signing off. Thank you, participants.
Sure.
Thank you, participants. We are leaving on behalf of IQAC and Government Mother Science PG College, Jen. Hope to see you again tomorrow, 27th of July at 11 a.m. Hope to see you again. We'll be sharing the links. Thank you very much. Thank you for being with us.